Let's you and I talk about the electrifying subject of electricity. And by the way, they ask some pretty tough questions these days on the A&P General Exam about electricity, but never fear, because by the time you and I get done, we're going to be able to answer every question with ease. We're going to take care of it in a flash here. All right, first of all, let's you and I get some definitions out of the way. What is electric current? Well, electric current is electrons in motion. Now, when the current flows in one direction only, it's called direct current. But current that reverses itself periodically is called alternating current. All right, now let's take a look at how you measure current flow, and it's measured in amperes. That's the unit of measurement of electrical current flow. How about, you might ask, little teeny tiny current flows? Well, that would be a milliampere, 1,000th of an ampere. That's written 0.001. Now, if you have a wire is typically called a conductor. Something that limits the flow of electricity is called resistance. So anything that limits the flow of electricity is called resistance. A wire is a conductor. Sometimes a wire has a little bit of resistance in it, however. And so what determines the amount of resistance is the length and the cross-sectional area of the wire. Now, if you decrease the length of the wire, you decrease the resistance. But if you make that wire bigger, give it a bigger cross-sectional area, you also decrease the resistance. So what makes low resistance in a wire is using a big wire, that makes sense, and a short wire. And those two things decrease the resistance in any kind of conductor, particularly a wire. All right, a resistor then is something that limits the flow of electricity. You can have various kinds of resistors, and sometimes you actually build a resistor into an electrical circuit. Now, here's what a resistor looks like that could be built into an electrical circuit. And what you're trying to do, again, is limit the flow of current with this resistor. Now, resistors can be of all different values, low value or high value, and that value is measured in ohms. We'll talk more about ohms later on. And resistors are generally classed as fixed or adjustable or variable depending on their construction and use. And a typical fixed resistor, like this one, consists of a small rod of carbon compound. So here's a typical fixed resistor. Now, an adjustable resistor is usually a small wire-wound type with a metal collar that can be moved along the resistance wire and it lets you vary the value of resistance placed in the circuit. And a variable resistor is arranged so that it can be changed in value any time by the operator, generally a knob. And variable resistors are commonly known as rheostats or potentiometers. Now let's take a look here on figure 17 and take a look at how a potentiometer is shown. Now, a potentiometer is a specific type of variable resistor. It's one in which the contact can be moved along to a different location and you can pull off the current at that particular point, thereby changing the amount of resistance. And that's a potentiometer. That's how it's shown. It's actually shown with a variable contact like so. Now, a potentiometer is a type of variable resistor. If you did not want to specify a potentiometer and just wanted to say variable resistor, you might take a look at figure 21, and here is a schematic indication of any kind of variable resistor, not specifically a potentiometer, and this is a variable resistor. So anytime you see an arrow going through an electrical component like you have here, that means it's a variable component, and in this particular case, it's a variable resistor. Now, resistors have to absorb a lot of electrical power. That's what they're doing, is absorbing and dissipating electrical power. And electrical power is measured in watts. We'll talk more about that later on. So what determines the wattage rating of a resistor? Well, the wattage rating of an electrical resistor is determined by its size. The bigger the resistor physically, the more power it can absorb. Now, what causes electrons to flow from one place to the other? Well, what it is called electromotive force. And this potential difference between two conductors is measured in volts. So how do you measure electromotive force? You measure it in volts. So that's the potential difference we're going to be talking about. It's measured in volts. That's what causes electrons to flow. And since EMF is measured in volts, you might guess that the FA might want you to know exactly what a volt is, and they do. A volt is the amount of EMF that causes a current rate of 1 ampere through a resistance of 1 ohm. You've got that, nothing to it. It's 1 volt causes a current rate of 1 ampere through a resistance of 1 ohm. Everything is 1. Now let's assume that you wanted to say, I've got 1,000 volts, and you wanted to be scientific about it. You wouldn't say 1,000 volts. You'd say, I have a 1 kilovolt, and that's 1,000 volts, and that prompts the FA to ask you a question. Let's assume the FA says you have 0.002 kilovolts. How many volts is that? All you have to do is multiply that 0.002 times 1,000, use your electronic calculator, and you find out that comes out to 2 volts. Now, the basic mathematical formula that describes how electricity works is referred to as Ohm's law. And let's you and I take a look at Ohm's law. First of all, I in this equation stands for the current, the flow of electrons in amperes. E stands for potential difference in volts, and R stands for resistance in ohms. And by the way, the electrical unit of resistance is an ohm, or ohms. And I remember one time an instructor said to me, "John, what's the electrical unit of resistance?" And I said, He says, "You're right." Okay, let's take a look at it. First of all, the relationship goes like this. The current flow is dependent on the voltage. The more volts, and E stands for electromotive force, and that's E is for volts. In this particular case, it's measured in volts. And the current flow, which is I, depends on the volts. If you have more electromotive force, or the volts are higher, there will be more current flow. What limits current flow is resistance. And the more resistance you have in ohms, the less current flow. So you can see the greater the ratio of volts to ohms, the more the current will be in amps. Now, you're going to need to know this electrical formula right here, this formula. And when you walk in to the FAA written exam to take the general test for the A&P, you should have this formula memorized, because you're going to need to use that. And what I recommend you do is sit down and write it down on a piece of paper when you walk in there right off. They will not let you carry this formula in on a piece of paper, but they will give you some blank sheets of paper, and they'll let you write it down. So I recommend you write it down on a sheet of paper as soon as you get in there. All right, first of all, we've talked about it. The current flow is determined by the ratio of volts to ohms, right there, or electromotive force, if you want to get fancy about it, to resistance. Now, you can work around with this formula mathematically. Multiply both sides by R, and you get E equals I times R. Now, what does that tell us? Well, what that tells us, if you're crossing a resistance, the voltage drop across that resistance is equal to the current times the resistance. We'll talk more about that later on, but the voltage drop across the resistance is equal to the current. There's the voltage drop, that's electromotive force, E, is equal to the current times the resistance. And then also you can play around with this some more, and you can divide each side, for instance, by I, and you get R equals E divided by I. Now, what does that tell us? Well, that tells us that the resistance is equal to the volts divided by, or the electromotive force, divided by the current in amps. So you'll need to know these three formulas. If you're good at algebra, knowing the first one will automatically give you the other two. But you need to be able to use those three formulas. Now, as you might guess, the FAA is going to ask you some questions about this. And once again, when you walk into that test, make sure you have that written down. Now, we said earlier, the voltage drop across the resistance is dependent on what? Well, it's dependent on the amperage of the circuit. Why? Once again, it's the same formula. The voltage drop, which is E, or the voltage difference or potential across the resistance, is equal to the amperage times resistance. So it's dependent on amperage. It's also dependent on resistance, but they ask you this on the test. So the correct answer on the test is it's dependent on amperage. All right, now, you can measure resistance with a device called an ohm meter. Now, here is an example of an ohm meter, and the way you use the ohm meter is you set the scale to the right level you want. Let's assume we have it set on R times 10. Well, what you do is read the resistance off the meter and then multiply it times 10. So let's assume we've done that. We're measuring a resistance, like the resistance we showed you earlier. And let's assume the needle reads 50, and we've set it to times 10. What is the resistance? And the answer is it'll be 500 ohms. Now let's take a look at figure 7 here, and we'll talk about how to use an ohm meter in a circuit to measure resistance. Well, we have a circuit here. There's a battery in it, but we have an open switch right here. So this is not a continuous circuit through the battery because that switch is open. And we have a few resistances. We've got a resistance over here and another resistance here and another one here. Now, you could put an ohm meter right here, and that's what this is, an ohm meter. And if you connect it like this, you'd be measuring all the way around these circuits like so, and you'd be measuring the total resistance of these three resistors right here. If you want to measure only the resistance of this resistor right here, what you could do is disconnect the terminal at D. If you had the terminal disconnected at D, then this would be the path or the circuit that the ohm meter would be measuring. Now, in this particular case, they're going to ask you a question on a test. They're going to say, take a look at figure 7 here. You have disconnected the ohm meter here at D, and what you have done or disconnected that terminal at D, and now you're measuring this particular resistor, but this resistor has a break in it. What would it read? Well, if it has a break in it, it would have no current going through at all because it's not possible. It would read infinite resistance. Now, there are two basic kinds of electrical circuits. One is a parallel circuit, which gives several paths for electricity to follow, and one is a series circuit. And here's a good example of a series circuit. A series circuit gives only one path for the electricity to follow, and you have resistances in that circuit, and the current must go through one, then another, and another in series. That's called a series circuit. It only gives one path for the electricity to follow. Now, no matter how many components are included in a series circuit, the current is the same intensity all throughout that circuit. So no matter how many components are included in that series circuit, the current is the same intensity all throughout the entire circuit. That's one of the things you need to know. The same current goes all the way throughout the entire circuit. Now, let's take a look at how you determine the total resistance in a series circuit. It's really pretty easy. All you do is add up all of the resistances individually. In a series circuit, to find the total resistance, we're going to call that R sub T. All you do is add up the resistances one at a time. There's resistance 1, resistance 2, resistance 3, 4, 5, however many they are. Add them up, and that gives you the total resistance. Let's take a look at a way they're going to ask us a question about this on the FA written exam. They're going to say a circuit has an applied voltage of, we'll say, 30 volts in a load consisting of 10 ohms in series with a 20 ohm resistor. Now, the question is, what is the voltage drop across the 10 ohm resistor? Now, how can we find that out? Well, the first thing we need to know to find that out is to find out the current going across that 10 ohm resistor. Now, the important thing to remember here is no matter how many components there are in this series circuit, the current going through each component is the same all the way through. So we can find the current for the total circuit real easy by using Ohm's law. Once we find the current, then we know the current for that particular 10 ohm resistor. Then we found the current for that 10 ohm resistor by using Ohm's law again. We can find the voltage drop across that resistor. Let's take a look at it. First of all, let's find the current for the entire circuit. We'll use Ohm's law, and the current is equal to the electromotive force in volts divided by the resistance in ohms. The volts they told us in this circuit was 30 volts. There were two resistors. All we have to do is add them together with a 10 ohm resistor and a 20 ohm resistor, and the total resistance was 30 ohms. Now, the volts is 30 volts, the resistance is 30 ohms. You divide, and the current is 1 amp or ampere, depending on how you want to pronounce it. It's optional, by the way. So we have 1 amp going through that circuit. Now, that one resistor also has 1 amp going through it. The 10 ohm resistor also has 1 amp going through it because all the components have the same amperage going through them, the same current. All right, so let's find out for that one resistor what the voltage drop is. Now remember we said earlier the voltage drop for a resistor is equal to the current times the resistance. And the current is 1 amp, the resistance is 10 times 10 is 10, so the voltage drop across that resistor is 10 volts. So you see, once you have Ohm's law nailed, you can solve these kinds of questions they're going to ask you on the test. Let's do another one. This is obviously too easy for everybody. And so let's assume you have 3 resistors of 3 ohms, 5 ohms, and 22 ohms. They're all in series. And let's assume you have a 28-volt circuit. Now, what is the current that will flow through the 3 ohm resistor? What's the current that will flow through that 3 ohm resistor? Well, once again, we need to figure out the total resistance, and then we're going to find the current flying through the whole circuit. Once we know the current through the whole circuit, it's the same all the way through each of those components in a series circuit. So let's find out the total resistance. All we have to do is add the resistances, because remember, in a series circuit, the total resistance is the sum of the individual resistances. And so we do this, and we get a total of, let's 3 plus 5 plus 22, and I get a total resistance of 30 ohms in that circuit. Now, once we know the total resistance in that circuit, now we can use Ohm's law and find the current in that circuit. And that's all we need to know, because the current for each resistor is exactly the same. That's one of the rules. Okay, here we are, Ohm's law. The current is equal to the electromotive force in volts divided by the resistance in ohms. The electromotive force in volts was 28. They told us that. We just figured out the total resistance for the circuit is 30 ohms. So the current for the entire circuit is 93 amps. And that's the answer to the question. Let's do another one. This time, they're getting a little bit tricky. They say you have a lead acid battery with 12 cells. And each cell is 2.1 volts per cell, and they're connected in series. And then they're going to say that you have a 10 amps furnished by that battery to a 2 ohm resistance, a circuit with a 2 ohm resistance. Now, if that's the setup, the question they're asking you is, what is the internal resistance of the battery? Oh my God. Never fear. It's a lot easier than that. Let's take a look at it. First of all, to find the total voltage of the battery when the cells are connected in series, you take the volts for each cell, which is 2.1, and multiply times the number of cells. We'll talk more about that later on, but if the battery is connected in series, its cells are, that's the formula for finding the voltage of the battery. You use your electronic calculator and take the 2.1 times the 12 cells, and you're going to get 25.2 volts. So the entire circuit, the electromotive potential of that battery is 25.2 volts. Now, let's figure out the resistance for the entire circuit. Formula for resistance is equal to volts, the electromotive force expressed in volts, divided by the current in amps, and that gives us the resistance. Now, if you remember, the voltage we just figured out is 25.2, and they told us that circuit had 10 amps in it. They told us that in the question. So what is the resistance? The total resistance of the circuit was 2.52 ohms. Now, wait a minute. They told us the resistance in the circuit was 2 ohms. Now we figured out mathematically the total resistance of the circuit is 2.52 ohms. What's the difference? And the difference is the internal resistance of the battery, and that's the question they're asking us in this case. So if the total circuit works out to 2.52 ohms and the resistor in this circuit is 2 ohms, then what's left must be the total resistance of the battery, the internal resistance of that battery, and it's 0.52 ohms. All we have to do is subtract, and we've got it figured out. All right, let's do another one. This time, however, let's talk about parallel circuits. Now, parallel circuits are different in that a parallel circuit provides several paths for the current to go through. So here we have a case in which the current can go this path or this path or this path, and that is a parallel circuit. Things are just sometimes a little bit more complicated in a parallel circuit, but the thing you need to know is that the voltage drop across any resistance in a parallel circuit, and in that group, is equal to the voltage drop across any other resistance. In other words, in a parallel circuit, the voltage across any resistance is equal to the voltage across any other resistance. All of the voltage drops across resistors in a parallel circuit are equal to each other. Now, let's take a look at another question. And to do that, let's take a look at figure 11 again. Now, let's take a good look at this before we get started. First of all, notice you have a 24-volt battery here, and you have 3 resistors, and they are in parallel. In other words, there are several paths for the current to take, 3 different paths in this particular case for the current to take. Now, the thing you need to know is the voltage drop across the entire circuit is the same throughout for the total circuit and for the voltage drop for each resistor. They're all equal. And so what is the voltage drop across the entire circuit? 24 volts. That means there's also the same voltage drop across resistor 1, resistor 2, and resistor 3. Now let's take a look at the question they're going to ask you. It's going to be very simple. The question is, what is the voltage drop across the 8 ohm resistor? Well, let's take a look at it one more time. It's 24 volts across each resistor, so for the 8 ohm resistor, it's got to be 24 volts. That's unbelievably easy. Now, here's another basic rule you need to know about parallel circuits, and that is the total current in that circuit is equal to the sum of the currents for the individual branches. So the total current is equal to the sum of these currents. So let's take a look at this drawing in more detail again. First of all, you take the current through this branch, the current through this branch, the current through this branch, total them together, and that is the total current. The current is the sum of the currents. Now let's you and I take a look at figure 13. And they're going to ask you, what is the total current flow in this circuit in figure 13 on page 6? Well, what we have to do is figure out the current on each of these different paths. There are 3 paths to go. You figure out the current for each one of those paths and then add them up for the total current, because there are 3 paths for the current to go. Now let's take a look at it. How many volts is this circuit? The circuit is 12 volts. So there is a 12-volt drop across each one of these resistances. We know that to begin with. We also know how many ohms each one of these resistances is, because it tells us here 30, 60, and 15. So to figure out the current for each path, all we have to do is use Ohm's law. So let's you and I take a look at that. Remember, there were 3 resistances. They were 30 ohms, 60 ohms, and 15 ohms. And to find the current, you take the volts, and the volts for all of them were 12 volts because that was the voltage drop across each resistor in that particular case. Take the volts, the E, or electromotive force, the volts, and divide it by the resistance, and that gives you the current. That's the basic Ohm's law that we said you need to know. All right, so all you have to do is do that for each one of these, 12 divided by 30, 12 divided by 60, and 12 divided by 15. And those are the 3 currents, the 3 different paths provided in that parallel circuit. Well, with your electronic calculator, 12 divided by 30 comes out to 0.4 amps. 12 divided by 60 comes out to 0.2 amps. 12 divided by 15 comes out to 0.8 amps. So to get the total current through the entire thing, you add them up. 8 and 2 is 10, and 4 makes 1.4 amps. So the total current through that circuit was 1.4 amps. Now that's the easy part. Now let's figure out the formula for the total resistance in a parallel circuit. And this is another formula, by the way, that you need to write down. So let's take a look at it. This is a little bit complicated, but never fear. By the time we get done, you're going to find it easy. Okay, the total resistance in the circuit is equal to a fraction that looks like this. It's 1 over these 3 individual fractions. And these 3 individual fractions consist of a numerator of 1 in each case and a denominator of the resistance for that particular resistor we're talking about. So the total resistance for the circuit is equal to 1 divided by these 3 fractions added together. And it's resistance 1, 1 over resistance 1, 1 over resistance 2, and 1 over resistance 3, etc., depending on how many resistances you have. Now you need to remember that the total resistance is equal to 1 over these 3 fractions. It's 1 over resistance 1, 1 over resistance 2, and 1 over resistance 3. And by the way, that's one of those things that you should write down when you take the written exam. And as soon as you walk down into there, write this formula down. We'll talk about this later on, which ones you should write down. And once again, they won't let you sneak them in. You can sneak them in your brain, and as soon as you get there, write them down. Now, there are some things that the mathematics of that formula will tell you, and one of them is this. If you have a parallel circuit, the total resistance of that circuit will be smaller than the smallest resistance in that circuit. So if you have 3 resistances in the circuit, the total resistance is going to be smaller than any one of those 3. And there's another thing that it'll tell you. Let's use light bulbs as an example. Let's assume you have a parallel circuit and there's 3 light bulbs in it, and one of the 3 bulbs is removed. What's going to happen to the total resistance? And the answer is the total resistance will become greater, because as you add more resistance, the total resistance becomes smaller. And that's mathematical formula tells you that. Now let's you and I take a look at Figure 8, Appendix 2, in the back of the book. And let's take a look at the question they're going to ask you here. First of all, you have this circuit with a battery in it, we'll say. And by the way, this is a fuse right here, and it has no resistance to it, and that's a switch up here. We'll talk more about these later on. All right, now what they're going to do is they're going to put an ohm meter in this circuit, and notice that there is a break right here. So if you put an ohm meter in this circuit at this particular point, you're basically going to be reading the total resistance of the parallel circuits consisting of resistance 1 and resistance 2. Resistance 3 has a break in it, so it's not involved in that. And so basically the question is, what is the total resistance of these two, this circuit consisting of these 2 parallel resistances? All right, let's take a look at it. The formula goes like this. The total resistance is equal to 1 over these 2 fractions. And it's 1 over resistance 1 divided by resistance 1 plus 1 divided by resistance 2. What are the numbers we're going to put in here? Well, each of these resistances on Figure 8 is 20 ohms. So now let's go back and take a look at the formulas, and it becomes the total resistance is 1 divided by these two fractions, 1 over 20 plus 1 over 20. Well, 120 plus another 1/20 comes out to what? Well, let's take a look at it. It comes out to 2/20. So now the total resistance is equal to 1 over 2/20. Wait a minute. What is 2/20 equal to? You got it. It's equal to 1/10. So now its resistance total is equal to 1 divided by 1/10. There's another way we could express that, and that is 1 divided by, with a division sign, 1/10. Now, if you want to get rid of the division sign, all you have to do is flip-flop the 1/10, and so the total resistance is equal to 1 times 10. And what's the total resistance of the circuit? And the answer is the total resistance is 10 ohms. You can see it right there. 10 times 1 is 10. Divided by 1 is still 10, and the answer is 10 ohms. All right, let's take a look at another one. They're going to say, all right, let's assume you have a circuit that contains 5 lamps in parallel. And 3 of those lamps have 6 ohms each, 2 lamps have 5 ohms each, and it's a 28-volt circuit. How many amps are in the circuit? Well, first of all, we need to find the total resistance in the circuit. Then we'll use Ohm's law and find out how many amps are in the circuit. And you need to be able to figure out what you need to know. Let's figure out the total resistance of the circuit first. And here you are. The total resistance is equal to 1 over these fractions. And the fractions are 3 resistances of 6 ohms, so it's 1 over 6 plus 1 over 6 plus 1 over 6. And 2 resistances of 5 ohms, so you got 2 more, the 1 over plus 1 over 5 plus 1 over 5. That is your formula. Boy, if you can remember that, this will be just duck soup for you. All right, now we have 3 of these 6s, so it's 3 6. So 1 6 plus 1 6 plus 1 6 comes out to 3 6. And 1/5 plus 1/5 comes out to 2/5. So now the resistance total is equal to 1 divided by these two fractions, 3 6 plus 2/5. Well, 3 6 is a half, and 2/5 still comes out to 2/5. So let's find out where we're going from there. Who knows where we're going from there? Well, where we're going is we're going to use our electronic calculator. And 1/2 is 0.5, 2/5 is 0.4. So now the total resistance is 1 divided by 0.5 plus 0.4. And the total resistance now is 1 divided by 0.9. You can see where we're going. Use your electronic calculator. And the total resistance is 1.11 ohms when you use your electronic calculator. Now we've got the total resistance. Let's use Ohm's law and figure out what the current is, because that's what the question is. What's the current? All right, the Ohm's law for current says you take the volts or electromotive force divided by the resistance, and that will give you the amps or the current. Now, they told us in the problem that it was a 28-volt circuit, and we just figured out the ohms was 1.11 in resistance, and so you take the 28 divided by 1.11, and you get 25.23 amps. All right, let's you and I do another one. And to do that, let's take a look at Figure 6 and Appendix 2 in the back of the book. And they're going to say, all right, let's assume you've put the ohm meter in the circuit right here like so. And what the ohm meter will be reading then is these parallel circuits. But they say, wait, hold the phone. Because if you look at R5, you'll notice it's disconnected. This resistance is disconnected at the junction with R3 and R4. So R5 is out of the picture. So the question is, what will this ohm meter read? Well, if you take a look at this, here's what the ohm meter will read. It will read the parallel circuits of R1, R2, and R3 and 4 are in series. They will be treated as one resistance. R5 is out of the picture, so the ohm meter will read these parallel circuits with R5 out of the picture, and R3 and 4 actually being in series with each other will treat them as one resistance. All right, now let's take a look at the mathematics of what we're going to have to do this. And here's the way it's going to work. The total resistance, and that's what we're asking here, is what will the ohm meter read? It'll read total resistance. The total resistance is equal to 1 divided by, and it's 1 over R1 because R1 was one resistance path, 1 over R2 because R2 was another resistance path. And remember, R3 and 4 are in series. We'll treat them as one resistor. So all we have to do is add up the value of those two together, so it's 1 over R3 plus R4. Now let's go back to that drawing one more time on figure 6 and get the numbers to put in there. And we have to have the numbers to do that. So let's you and I go back to figure 6, appendix 2, and get those numbers. And we do that. We can look in here real close, and I think R1 comes out to, well, let's take a little tighter look at that. R1 comes out to 12 ohms, R2 is 6 ohms, R3 is 6 ohms, R4 is 6 ohms, and we can ignore R5 because it's out of the picture. Now, let's go back to the math and fill in those things. R1 is 12 ohms, R2 is 6 ohms, and R3 and 4 each 6 ohms. And so now you have the total resistance is 1 over the fraction 1/12 plus 1/6 plus the fraction 1 over 6 plus 6. You can see what's going to happen next. We'll add that 6 plus 6 together, and everything's the same. Now it becomes 1 over 12. Let's take a look at the next one down here that we're going to. And we have now RT is equal to 1 over the fraction 1/12 plus 1/6, but that's 2/12 plus 1/12 because that became 1/12. And so 1 plus 2 plus 1 comes out to 4/12. So now the total resistance is equal to 1 over the fraction 4 divided by 12. Let's take a look at the next item down there again. And 1 over 4 divided by 12, well, 4 divided by 12 is 1/3, so now it becomes 1 over 1/3. Now, another way to express 1 over 1/3 would be the total resistance equal to 1 divided by 1/3. And if you want to get rid of that division sign, all you have to do is flip-flop these two, and the total resistance becomes 1 times 3 over 1, and the total resistance is 3 ohms. Now, the thing you need to remember about that question is that you use the formula for parallel resistors, but if you have resistors in series, you don't have to use that formula. You just add them together as far as those resistors that are in series are concerned. Now let's make life a little more complicated because after all, that's what the FAA is going to do to you in the test, so we might as well do it now. So let's take a look at figure 14, appendix 2 in the back of the book. And you see a circuit that looks like this. Oh my God, this is complicated. This is a combination of series and parallel circuits. First of all, you start off with this circuit right here, this resistance in series. Then you have the paths split out, and you have 3 paths that the electricity can go with a resistance in each one of them. Then it goes back to 1 path and another series resistance there. So what we're going to have to do is convert this parallel circuit into 1 total resistance, and then all we have is 3 series resistances right there. So let's convert this 1 parallel resistance, first of all, this parallel circuit, into 1 single total resistance. And to do that, let's get the numbers. Resistance 2, if you look at the ohms there, I believe comes out to 4 ohms. And resistance 3 comes out to 6 ohms. And let's take a look over here and see what resistance 4 comes out to, 12 ohms. So what we want to do is take that path right now and convert that into a total resistance. And then again, we get done with that, we're going to add it to these series resistances over here. All right, let's convert that path we just talked about into, if you don't mind, a total resistance. And total resistance for a parallel circuit looks like this. It's 1 over these fractions, and the resistances were 4 ohms, 6 ohms, and 12 ohms. So the fractions become 1/4 plus 1/6 plus 1/12. All right, so now the total resistance for those 3 resistors in parallel become 1 over 1/4 can be converted to 3/12. We're converting these all to 12ths so we can add them together. And 1/6 becomes 2/12, and 1/12 still stays 1/12. Now let's add them together. 3 plus 2 plus 1 comes out to 6/12. So now the total resistance is 1 over 6/12. Back in the old days, 6/12 used to be 1/2. I think it still is. So now we'll call that 1 over 1/2. But let's express that a different way. We'll call it 1 divided by 1/2. It's the same thing. Now, if you want to get rid of the division sign, all you do is flip-flop this fraction. It's 1 times 2 over 1. And the resistance for those 3 resistors in parallel is 2 ohms. Now let's go back and look at the drawing again and see where we go from here. What we did is we figured out the total resistance for these parallel resistors was 2 ohms. Now we take that 2 ohms and the the path of the current goes like this. It goes through this resistance up here, and then through the 2 ohms, and this resistance down here, and then back. So let's figure out what the resistance is total, and all we have to do is add these up. So let's take a look at that resistance right there and see if we can read the number off that chart. And if you look at resistance 1, we get in there real tight and take a look at it and see what it says. And I think it says that's 5 ohms. And now let's take a look at the bottom resistance down there and see how many ohms that is. And that is 10 ohms. So now we have 2 ohms for the parallel circuit. And the series resistance of 2 ohms and 5 ohms, let's take a look at the math. It's 2 ohms plus 5 ohms plus 10 ohms. And so the total resistance of the entire circuit is 17 ohms. All right, that was complicated, wasn't it? Let's do it more complicated. And to make it more complicated, let's take a look at Figure 12 in Appendix 2 in the back of the book. And here is another even more complicated circuit. And the circuit looks a little bit like this. First of all, you start off here and you have a resistance in series, and then you have a parallel path. You can go 2 different directions, and then you have another 2 paths you could take here, and then you come back here, go through a switch, go through a fuse, and then back. And the fuse, of course, has no resistance at all as far as we're concerned. All right, now the way we're going to do this is we're going to have to try and resolve these parallel paths into a total resistance. So the first one is this one on the right-hand side over here. So let's take these 2 resistances as a parallel path and figure them out as a total resistance. And let's take a look here and see if we're going to read these numbers off these resistances. And I believe the resistance number 4 is 12 ohms. Resistance number 5 is 6 ohms. So let you and I, first of all, mathematically convert those into a total resistance. And so the total resistance is 1 over, and it was 12 ohms and 6 ohms, so the fraction's 1/12 plus 1/6. And of course, we can convert that 1/6 to 2/12 so we can add these together. So now the total resistance is 1 over 1/12 plus 2/12. And I believe if you look down there a little further, that's going to come out to 3/12. So let's see if it does. And it does. The total resistance is 1 over 3/12. And 3/12 is 1/4. So the total resistance is 1 over 1/4. Do you think that there's going to be another way to express that? There sure is. And it's 1 divided by 1/4. If you want to get rid of the division sign, you just simply flip-flop the fraction, and it's 1 times 4 over 1. So that path, the total resistance, is 4 ohms. Let's you and I go back and look at Figure 12 one more time. And what we have just done, we have just made this path right here, we've made a total resistance out of that of 4 ohms. So now if you look at where this current can go, current starts out here, we have a resistor here, and now we have a resistor here and a resistor here. We have parallel paths, or more than one path, but we've reduced this to one path. So what we have to do now is add this resistance to this resistance, and that gives us a path here, and then we'll have to figure out these 2 paths right here. This resistance, R2, is 12 ohms, and we just figured out that the resistance we were working on just now was 4 ohms. So let's take a look at the math of adding those 2 together, and all we have to do is add those 2 in series together. It's 4 ohms plus 12 ohms, and then it comes out to 16 ohms. So now let's go back and look at the drawing and see where we're going from there. All right, first of all, we have said now that we have this first path, we have a resistor here, and we have a path here. The total path is 16 ohms, and we have another path here that it could go, which in this case, if you look at that carefully, is 4 ohms. So now we need to convert these 2 paths, these 2 paths here and this path, into one total resistance. And so what we have is, if you remember, 16 ohms and 4 ohms. So let's take a look at the math for converting those paths into one total resistance. And we have 1 over, and it was 16 ohms and 4 ohms, so the fractions are 1 over 1 divided by 16 plus 1 divided by 4. And we can convert that 1/4 into 16ths. That's 4/16. Now we can add them together, and so it becomes 1 over 5/16. Do you think that there's going to be another way of expressing that? Well, I bet if you look down there, you'll find that works out to 1 divided by 5/16. If you want to get rid of the fraction, you flip-flop it, and it's 1 times 16/5, or 3.2 ohms. Now let's take a look at where we're going to go from there. And to do that, let's you and I take a look at the drawing one more time. So here we are looking at that drawing. one more time. And the paths we have just figured out is we have 3.2 ohms for this entire pathway from here to here all the way. So now all we have is this resistance here plus this entire mess now has been resolved to 3.2 ohms. So all we have to do is add them together because they're series circuits. So let's take a look at the mathematics for adding those two together. And when you do that, you get 3.2 plus 18, and you get 21.2 ohms. Let's one more time look at that drawing to see what we did on figure 12. And what we did is we tried to resolve these parallel paths into a total resistance. We said this is a series resistance. There's only one path here, but now we have two paths. And if we go over here, we have a path with these two together. So we resolved these two right here into a total resistance. Then when we got done with that, we said, all right, now this is a series. So we added the total resistance here to this resistance here, which is in series, added them together, and we made them series. But now you have to take this whole mess and take these two paths and make a total resistance out of them. And we did that, and now all we had then was two series resistances to add together. See, there's nothing to that stuff. We've been doing pretty tough questions. It's time for you and I to do an easy one. So let's take a look at figure 11. And the question is going to be, what is the total current flowing in the wire between points C and D? Well, let's take a look at figure 11. First of all, we have a 24-volt battery, and then we have a fuse right here, which has no resistance as far as we're concerned. And then C and D is what we're talking about. So we'd have the current going, it could go this way, or the current goes this way. Of course, it goes both ways. And then we have these two parallel resistances and then back. So all we have to do to find out the total current, we have to figure out the resistance of this circuit that involves the wire between C and D. Now we know the volts, and if we know the resistance for that path, then we'd know the current because we'd use Ohm's law to figure that out. So all we have to do is resolve this parallel circuit into a total resistance. And we have 10 ohms and 40 ohms. Let's figure out the resistance. Then we'll use Ohm's law to figure out the current. See, I told you this was an easy one, so let's take a look at the math on it. It's resistance 2 and resistance 3. So the total resistance for resistance 2 and 3 goes like this. 1 over the fractions 1 divided by resistance 2 plus 1 divided by resistance 3. And the resistances were 10 ohms and 40 ohms, so it becomes 1 over 1/10 plus 1/40. Now let's take a look at how we're going to solve the rest of this down here. To add these two together, we'll convert that 1/10 into 4/40, so we can add them together. So the total resistance is 1 over 4/40 plus 1/40, and we add those two together, and the total resistance is 1 over 5/40. Now, let's take a look at what 5/40 works out to. Well, first of all, instead of dividing it 1 over 5/40, let's express it another way, 1 divided by 5/40. And to get rid of that division sign, all we have to do is flip-flop the fraction, and it's 1 times 40 divided by 5, and we can use a calculator for that. And 40 divided by 5 comes out to 8, and the resistance is 8 ohms. Now, Ohm's law says if we know the volts, which was 24, we know the resistance, which is 8, to get the current, all you have to do is divide the volts by the resistance. So 24 divided by 8, and we'll take a look and see what the current is. And the current on the wire between C and D was 3 amps. And that is back to an easy one again. Now, this one drawing is going to cover 3 concepts the FAA wants you to know about, and that is diodes, rectifiers, and transformers. Let's talk about diodes first. A diode is basically an electrical check valve. It allows the current to flow in only one direction. So you have the current going like so. It goes past the diode, but it can't go back. And that is a diode, and that's the purpose of it. A diode can either be a tube or a transistor, and this is a symbol for a transistor diode like so. Now, a diode, then, you can think of as a check valve, and they're used in rectifiers. Now, a rectifier is a circuit that converts alternating current, which reverses itself periodically, to direct current. You can see how it would work. If you have alternating current that's reversing itself, this diode lets the current go this direction, but not that direction. So what you have now is intermittent direct current. Now, if you had opposite phase alternating current down here reversing itself, this diode lets it only go in one direction. And if it's the opposite phase, it's going at the different time than this is, so that these two join to be direct current going out this direction, and that's a rectifier, and that's the whole purpose of it, and diodes are used in rectifiers. Now here is a special kind of diode known as a Zener diode. Now a Zener diode is one that will conduct electricity only under certain voltage conditions, and a typical application for a Zener diode would be as a voltage regulator. So that is a special kind of diode known as a Zener diode. Now here is a transformer. Now a transformer actually is two coils of wire normally wrapped around the same bar or wrapped over the top of each other. And if you have a small coil in the primary circuit and more wraps or more turns in the secondary circuit, you step up the voltage. And by the way, if you step up the voltage, we'll say from 1 to 4 here, you would step down the current by the same ratio. That's one of the things you need to know about a transformer. When it steps up the voltage by a ratio, it steps the current down by that same ratio. Now here's a question they're going to ask you about this on the test. They're going to say, all right, let's assume you have a transformer with a step-up ratio of 5 to 1, and the primary voltage is 24 volts. Well, the secondary voltage would be 5 times that. But the primary amperage is what they're going to ask you what it was, because they're telling you the secondary amperage is 0.2 amps. Well, if the secondary amperage is 0.2 amps, it gets stepped down by the same ratio that the voltage got stepped up. So the primary amperage had to be 5 times 0.2 amps, or the answer is 1 amp. And that's a typical way they're going to ask you questions about this on the test. All right, now let's talk about my favorite subject, power. And the question is, what is power? Well, power is the rate of doing work. And there is a formula for electrical power, and here it is. Electrical power, and by the way, it's measured in watts, and we'll talk about that in just a few seconds. Electrical power is the current flow in amps times the electromotive force in volts. It's amps times volts, and that gives you power. Now, mathematically, you can play around with this a little bit, and you can divide each side by E, and you find that the current is equal to the power divided by the electromotive force in volts. You could also play around with this and divide each side by I, and you'd find out that the volts, or electromotive force, is equal to the power divided by the current. Now, the two that you need to know for the FA written exam are these top two, and we'll work with those for quite a bit. Now, once again, what is the unit used to express electrical power? And the answer is the unit of electrical power is a watt. Now, I had an instructor ask me that question. John, he said, what is a unit of electrical power? I said, what? He says, you're right. All right, now let's take a look at a question the FA is going to ask you about this on the test. They're going to say, let's assume you have a 24-volt source, and it furnishes 48 watts to a parallel circuit, and there are 4 resistors of equal value. What is the voltage drop across each resistor? Now, I am sure that you have heard of the concept of blowing smoke. This is a wonderful example of blowing smoke, because the 48 watts in this question has nothing whatsoever to do with it. If you have a parallel circuit, the voltage drop across each resistor is identical to the total voltage drop. What is the total voltage drop? 24 volts. What's the voltage drop across each resistor? 24 volts. What did the 48 watts have to do with it? Absolutely nothing. And here is yet another case of blowing smoke on the same subject. The FA just loves to blow smoke. Here you have a parallel circuit. You have a cabin entry light that is 10 watts and a dome light that is 20 watts. And they are wired in parallel with each other across a 30-volt source. Now the question is, if you measure the voltage drop across the 10-watt bulb, what will that tell you about the voltage drop across the 20-watt bulb? And the answer is it will be equal, because these are just resistances in the circuit, and the voltage drop across all resistances that are parallel to each other in a circuit is the same. And what did the wattage have to do with it? Absolutely nothing. Now, let's take a look at another question that the watts does have something to do with it. You have a 48-volt source, 192 watts in a parallel circuit, and you have 3 resistors of equal value. What's the value of each resistor. Now let's stop right here and take a look at this and see how we're going to figure this out. First of all, we need to know the total current through the circuit. Then after we've figured out the total current through the circuit, then we're going to figure out what the resistance is for the entire group. So let's figure out, first of all, the total current through the circuit. To do that, we'll use this law right here. You've seen that before. It's the power law. Okay, first of all, the current is equal to the power in watts divided by the electromotive force in volts. The power in watts was 192, and the volts was 48, and so the current in amperes was 4 amperes. So now we know the current in amperes. All right, now let's take a look at what the total resistance is. The total resistance for the entire circuit is equal to the electromotive force, which is E, which is volts, divided by the current in amps. The volts was 48, the current in amps was 4, the total resistance was 12 ohms. Now that total resistance is made up of 3 identical resistors. So if we want to know the formula for 3 identical resistors providing a total resistance, we know that this total resistance is 12 ohms. Here's how it got there. It's 1 over the 3 fractions, resistance 1 plus resistance 2 plus resistance 3, 1 over those as fractions. Okay? Now, if the denominators are all the same, you can add fractions together. So that 12 ohms as a total resistance can also be expressed as 1 over the fraction 3 divided by the resistance value for each one of those resistances. Now we can simplify that expression just a little bit. The 12 ohms total resistance is equal to 1 divided by 3 over the individual resistances. Now we want to get rid of the division sign. All we have to do is flip-flop that fraction, as you know. So that total resistance is equal to 1 times the individual resistances divided by 3. And now we can begin to see that we can figure out the value of each individual resistance. And so that total resistance of 12 ohms is equal to R, that's the individual resistance of each resistor, divided by 3. Multiply each side by 3, and you find out the value of R is 36 ohms. The value of each one of those individual resistors is 36 ohms. All right, so what we did first of all is figured out the current for the entire circuit. Then we figured out the resistance, here current for the entire circuit, then the resistance for the entire circuit. Then we used the formula for parallel resistance, parallel circuits, and then we found out the value of R, which is each one of those resistances. You guys have got it made. You're doing fantastic. All right. What's the operating resistance, the next question says, of a 30-watt bulb in a 28-volt system? And the question is, what is the resistance? Well, first of all, let's figure out the current, and then we'll figure out the resistance. That makes it pretty easy. The current works out at a formula like this. Here's the current is equal to the power in watts divided by the volts. Power in watts is 30, volts is 28, the current is 1.07 amps. Once we know the current, then we can figure out the resistance with Ohm's law. And resistance equals the volts divided by the amps. The volts was 28, the amps is 1.07, and the resistance is 26.17. And that is the answer to that question. Let's take a look at another question involving parallel circuits. The FAA is trying to make your life complicated with these parallel circuits, and they're doing it. Let's take a look at the question they're going to ask. First of all, they say that you have a 24-volt source, and that's the voltage that's required to furnish 48 watts to a parallel circuit, and this circuit contains 2 resistors of equal value. Now the question is, what is the value of each resistor? Oh my God. We can figure it out, never fear. Let's take a look at another bit of information they give you that's extremely valuable. They tell you that the total resistance in this circuit, they give you this formula. The total resistance is equal to the voltage squared divided by the power. So they give you that formula. That's a tremendous help. So now all we have to do is plug in some numbers. We know that the total resistance is equal to voltage squared divided by power, and the voltage we know was 24, and the power was 48 watts. So you take the 24 times 24 divided by 48, you do that with your electronic calculator, and you're going to get 12 ohms. And so right now we know the total resistance in that circuit is 12 ohms. Now we talked about earlier the formula for the resistance when they're in parallel in a circuit, and it's 1 divided by 1 over R plus 1 over R. And in this case these resistors are equal to each other, so this value of R is the same in each case. So that 12 ohms resistance, that's that total resistance, is equal to 1 divided by, and you can factor out 1 over R here, and it's 1 plus 1 times the quantity, 1 divided by R, and it's the same as 1 plus 1, that quantity, divided by R. So we factored out that 1 divided by R, and it's 1 plus 1, that quantity, times 1 divided by R, which is the same as anything divided by R over R. And now we have the total resistance, that was 12 ohms, is equal to 1 over, and this is 1 plus 1, that comes out to 2. 2 divided by R. So that's all there is to it. And so the total resistance is 1 divided by 2 divided by R. Well, to multiply, all we have to do is flip this. So it's total resistance at 12 ohms is equal to 1 times R divided by 2. Okay, 1 times both of these means the total resistance is equal to R divided by 2. That's all there is to it. And the total resistance was 12 ohms, and so 12 equals R divided by 2. Multiply both sides by 2, and R comes out to 24 ohms. The value of each resistor comes out to exactly 24 ohms. Well, let's do it a little bit more complicated. Question is, how much power must a 24-volt generator furnish to a system with the following loads? And this is the following loads right here. We have a 24-volt generator. You have one motor that's 75% efficient, and it's 1/5 horsepower. You have 3 position lights in the airplane. They're 20 watts each. You have one heating element that is 5 amps, and you have one anti-collision light that is 3 amps. How much power is required? Well, we have watts here, we have horsepower here, we have amps here. Let's convert this all into watts. First of all, let's figure out the motor. Now, there is something they give you that you absolutely have to have, and don't panic because you don't know this, because they tell you this. What they tell you is that 1 horsepower is 746 watts, and you do not need to memorize that. They tell you that when they give you the question. Now, this motor was only 75% efficient, so in order to get 1 horsepower, you actually have to have 746 watts divided by 0.75, or 75%. That would come out actually closer to about 1,000 watts. And we weren't actually looking for 1 horsepower in this case. We were looking for 1/5 horsepower. So what we'll do is we'll take 1/5 times 746 divided by 0.75, and you find out this motor requires 199 watts. Now, they told us also they had 3 position lights, and each one of those was 20 watts, so 3 times 20 is 60 watts. And they also told us we had a heating element, but they said the heating element was 5 amps, not watts. And so we need to convert that into watts, which is power. And so what you do is use this formula for power, and you take the current times the voltage, or the electromotive force, and that gives you the power in watts. So it was 5 amps times the 24 volts gives us 120 watts. All right, now let's take a look at the rest down there. The anti-collision light was 3 amps. And a 24-volt system, so we can do the same thing. 3 times 24 is 72 watts. And all we have to do is total those up. We had 199 for the motor. The position lights was 60 watts. The heating element was 120 watts. The anti-collision light was 72 watts. And the total of that is 451 watts. So if you know these formulas, you got it nailed. They're just asking you to be able to multiply volts times amps to get watts. And that's all we had to do in that particular case. Now, here's a question the FAA is going to ask you that I think is actually kind of fun. It involves 3 different types of electrical systems, and it says, which one of these do you think will require the most electrical power? Well, let's take a look at each of these 3 situations one at a time. In the first one here, you have 4 30-watt lamps, and they're arranged in a 12-volt parallel circuit. Now, they ask you about power, and what's the term you use to describe power? It's watts. So they've already told you you have 4 30-watt lamps, so the total power is going to be 4 times 30, or 120 watts right there, and that is deceptively simple, so the first circuit is 120 watts. Well, that's pretty easy. Let's do another one. Now you have a 24-volt anti-collision light circuit. It consists of 2 light assemblies which require 3 amps each during operation. Well, let's take a look at this. First of all, power, as you remember, is amps times volts. Well, we have 3 amps and 24 volts. So this is 3 times 24 in each circuit, and that's the power required in each circuit. It's the amps times the volts. And we have 2 of those circuits, so to figure out the power here, 2 times 3 times 24, that's the power in each circuit, equals 144 watts. So that's a little bit more. That's 144 watts. So let's take a look at the third situation they're going to ask you about. Here you have a motor that produces 1/5 horsepower. It's a 24-volt motor that's only 75% efficient, and they tell you that 1 horsepower is equal to 746 watts. That's a key bit of information you have to know, but they already told you that. So let's take a look at it. First of all, we have 1 horsepower is 746 watts, but this motor is only 75% efficient. So to produce horsepower, it's 746 divided by 0.75. So that would give you 1 horsepower. But we're only talking about 1/5 horsepower, so we'll multiply that times 1/5. So the formula will be 1/5 times the power required for 1 horsepower, 746 watts for 1 horsepower, but it's only 75% efficient. And then you multiply that out and you get 199 watts. That's the one that requires the most power, and I think that's a fun question. Now here's another question involving power they're going to ask you about on the test. They're going to say, let's assume that you have a 12-volt electric motor and that it has a 1,000 watt input and a 1 horsepower output. So you can see it's pretty efficient. Now let's assume that you had a 24-volt motor with 1 horsepower output that had the same efficiency ratio. The question is, how many watts would be required? And the answer is the same 1,000 watts. If it has the same efficiency ratio, watts to horsepower, it's going to be the same down here, still 1,000 watts. And whether it's 12 volt or 24 volt doesn't make any difference. Now let me ask you a question. Do you think that even in the most remote stretches of your imagination that the FAA could ever be deceptive? You bet they can, and here is a case in point. They have a question like this, they give you this information. They tell you that you have a 1 horsepower, 24 volt DC electric motor, and that this electric motor is 80% efficient, and it requires 932.5 watts to produce that 1 horsepower. They give you that information, then they ask you this question. They're going to ask you, how much power will a 1 horsepower, 12 volt DC electric motor require if it's 75% efficient? How much horsepower or watts will be required to produce that 1 horsepower? And they also tell you that 1 horsepower equals 746 watts. Now you might look at this and say, hold it, wait a minute. What does this top part have to do with this question? I've got the information I need right here, don't I? And the answer is, this top part had absolutely nothing to do with the question. They just threw that in there to confuse you. It works, doesn't it? Well, now, if this engine, this motor, were 100% efficient, it would take 746 watts to produce this 1 horsepower. But in this particular case, we're told it's 75% efficient. So all you have to do is take that 746 watts divided by 0.75, and you're going to find out that it's going to take about 1,000 watts to produce 1 horsepower, actually 994.7 watts, and you have produced 1 horsepower, and that is a case of being very tricky. Let's do another one. This time they're going to say you have a 14 ohm resistor to be installed in a series circuit carrying 0.05 amps. Now the question is, what is the power required to be dissipated by that resistor? All right, let's take a look at it. First of all, we want to know how many volts are in the circuit before we can multiply volts times amps to get watts. All right, to find out how many volts are in the circuit, you use this formula. Volts is electromotive force equals the current, which is I, times the resistance. The current was 0.05 amps, and the resistance was 14 ohms, and you multiply that out, and we have 0.7 volts. Now we have the information to find out power, and so you take the volts, which was 0.7, and multiply it times the current, which is 0.05, and 0.05 times 0.7 equals 0.035 watts, and that's 35,000th of a watt. Another way to express that is 35 milliwatts, because 1 milliwatt is 1,000th of a watt. All right, let's do another one. This time, let's take a look at Figure 8, Appendix 2, the FAA's book, and they give you a circuit like this, and they say, how much power is being furnished to this circuit? Well, once again, first of all, you have to find the voltage before you can multiply the volts times the amps. Well, let's call this a generator. Let's call this a 23 amp meter here. It's an ammeter, and it's measuring 23 amps and a resistance of 5 ohms. And so we know the amps and we know the resistance. So now let's take a look at what we need to do to find volts. Well, if you remember the formula, it's very simple. Volts equals the amps times the resistance. And we have 23 amps and resistance of 5 ohms. It's 115 volts when you multiply that out. To find the power, you multiply the current times the voltage, and the current was 23 amps, the voltage was 115, multiply that out, and it's 2,645 watts. All right, it's getting simpler and simpler and simpler, isn't it? Let's do another one. Let's assume that you have a 30-volt, 1/2 horsepower motor that is 85% efficiency. The question is, how many amps will it draw? Well, first of all, let's find out how many watts this motor is, and then we can figure out how many amps it is. All right, to find out how many watts, we have a 1/2 horsepower. They will tell you, once again, that 1 horsepower is 746 watts. You do not need to memorize that. Don't worry about that. And it's 85% efficient, so to produce 1 horsepower at 85% efficiency, it would be 746 divided by 0.85. We only want to produce 1/2 horsepower, so we multiply that times 1/2. So it's 1/2 times 746 divided by 0.85, and it's 438.8 watts for this motor. But hold the phone, they asked us for amps, and the formula for amps is the current equals the power in watts divided by the electromotive force in volts, and the power is 438.8 divided by the 30 volts, and so the current is 14.6 amps, and that's the answer to that question. Now, before we wrap up DC current, I want to cover those formulas that you need to have in your mind when you walk into that test room. Let's take a look at them. First of all, if you remember, you need to know Ohm's law. And Ohm's law is current in amps is equal to electromotive force in volts divided by resistance in ohms. Now, if you know that, you can get the other two in Ohm's law if you're good with algebra. But the other two are that the electromotive force in volts is equal to the current in amps times the resistance in ohms, and the resistance in ohms is equal to the electromotive force in volts divided by the current in amps. You need to know those three. If you got algebra nailed, then all you have to do is know the first one and you can figure out the other two. Now let's take a look at the formulas for resistance. First of all, resistance in series. To find the total resistance in the circuit, just add up the individual resistances, however many there are. Resistances in parallel. To find the total resistance, you use this formula. It's 1 divided by these fractions. 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. If you know those two resistance formulas, you've got that taken care of. And finally, let's take a look at the formula for power. Power is equal to, and it's in watts by the way, equal to the current in amps times the electromotive force in volts. And the other formula for power, you can figure it out algebraically. If you know this one, you can figure this one out. But the other one is that the current in amps is equal to the power in watts divided by the electromotive force in volts. Now, if you've got everything that we've talked about, you have everything you need to know about DC current on the general exam. Now, let's see if you and I can figure out AC current or alternating current. Now, alternating current is different than direct current. Direct current goes only in one direction. Well, alternating current goes in one direction, then it reverses itself, goes the other direction. Then it reverses itself, goes the other direction. Then it reverses itself and goes the other direction. I think you get the idea. Alternating current periodically changes in direction and continuously changes in its magnitude. Now, if you look at it in a sine wave, you'd see what I'm talking about. Here's what it would look like in an oscilloscope. And this is a sine wave on an oscilloscope, and it describes or it shows you what alternating current looks like. Now, here's the midpoint, and you have the alternating current first going one direction and very low intensity, and then it increases its intensity, and then it begins to level off, gets weaker, then changes direction, goes the other direction, gets stronger in intensity the other direction, weakens off, and so on, back and forth and back and forth. Now, they're going to ask you on the test, how would you describe alternating current? Here's how you define alternating current. It's current that periodically changes direction and continuously changes in magnitude. And that's a picture of what alternating current looks like right there. Now, there are three values regarding alternating current that should be considered. They're instantaneous, maximum, and effective. Let's take a look at them. First of all, the instantaneous value of alternating current is the value of the induced current or voltage flowing at any instant. And let's take a look at that in writing here. The instantaneous value is the value of voltage or current flowing at any instant. That's the instantaneous value. In other words, at any particular time, you can figure out what the value of the current is. That's the instantaneous value. The next thing we want to see in writing is the maximum value. And the maximum value is the largest instantaneous value. It's the peaks here. That's the maximum value, the largest instantaneous value. Finally, what's really important is the effective value. And the effective value is the direct current to produce an equal heating effect. In other words, if you're trying to heat up the circuit, how much current would you have to do in direct current to produce the same values as this particular alternating current? And that's the effective value. And by the way, unless somebody says otherwise, when they talk about the value, they're talking about an effective value. And as a rule, by the way, the effective value, would you think it would be more or less than the instantaneous value? And the answer is the effective value is less than the maximum instantaneous value, because the effective value is kind of an average. It's called a root mean squared, but it's really an average, and it's less than the peaks or the maximum instantaneous voltage. So the effective voltage would be less. Now, once again, unless otherwise specified, any values given will be effective values, unless somebody says otherwise. And that's either for current or voltage in an AC circuit, and that's what you assume is effective values. Let's talk about lines of force, because that's a concept that will be useful later on. Anytime you pass a current through a wire, you create a magnetic field around that wire, and that's called lines of magnetic force around that wire, and that's what we're talking about. And when you apply a voltage to put a current through a wire, first what happens is you create a magnetic field, and that actually delays the flow of current for just a little bit, and so the current doesn't flow for a while. Then when the magnetic field is created, the current flows. If you happen to apply alternating current, what happens is first you have a voltage applied in this direction. There's a little delay while the field is being created, and then when that voltage drops off, the current still flows for a while the field collapses. Then you apply a voltage in the other direction. There's a delay while the magnetic field gets created and so on. But you have a constantly collapsing and expanding magnetic field when you run alternating current through a wire. Now, if you want to intensify that magnetic field, you can do something very, very creative. What you can do is take that wire and wrap it into a coil, and you concentrate or intensify that magnetic field and get a much stronger magnetic field. If you want that magnetic field to be even stronger yet, what you can do is put an iron core in here, and that really concentrates the magnetic field. And in fact, one of the things you want to know is magnetic lines of force pass most readily through iron when compared, we'll say, with copper or aluminum, and therefore putting an iron core in here really concentrates the magnetic field. Now, another bit of information you might want to know is that if you took an electromagnet, let's assume you don't have any current through this wire right now, and you just take any kind of magnet for that matter, take a magnet and wave it by this wire. What you'll do is as you wave the magnet by this coil of wire, you'll create a current in that wire. Of course, that's the basis on which a generator works, and that's one way of creating a current, is just take a magnet and pass it by a wire, and you'll create a current in that wire. Now let's get a little more complicated. Let's have two coils of wire. Here we have a coil of wire with an iron core and another coil of wire with an iron core through it. In fact, we'll have the iron cores be connected, but these two coils of wire will not have connected electrically in any way at all. Now let's assume that we put an alternating current in this coil of wire. What happens is we're going to create a magnetic field that keeps expanding and collapsing. Well, we said if you run a magnetic field past a coil of wire, you could create a current in that other coil of wire, and that's exactly what happens here. The expanding and collapsing field from this coil of wire creates a current in this coil of wire, even though they are not connected to each other electrically in any way. So transfer of electrical energy from one conductor to another without the aid of any kind of electrical connections between the two, that is called inductance. And this arrangement is called a transformer, where one coil creates a current in another coil over here, and the basis for transformer operation in the use of alternating current is what is known as mutual inductance. A magnetic field from one coil induces a current in the other, and that's called mutual inductance. So when you create a coil of wire in a circuit, you are creating what they call an inductor in the circuit. Now let's assume that we have an electrical circuit and we have a couple coils of wire. If you have one after the other, then you have more inductance. In fact, when you put two inductors in a circuit, what happens is the total inductance is equal to the sum of the individual inductances. So now we have two coils, we have twice as much inductance. That means twice as much magnetic field, and in some conditions twice as much impedance to the flow of current while that field is being created. Okay, now let's assume instead of having these in series, as this is, one after the other, you put these inductances in parallel with each other. Now you're going to find that there is less inductance totally. How much less inductance totally is there? Well, the total inductance is less than the lowest rated inductor of all of these. Of any one of these, is less than in any of them. This is putting inductances in parallel. Now, we said earlier, anytime you have inductance, a coil of wire, it tends to impede the flow of current. What's that called? Well, that is called inductive reactance. Let's take a look at the words for that. That's called inductive reactance, and it's measured in ohms. Why is it measured in ohms? Because it slows down the current, it impedes the flow of current just the way resistance does. And so it's called inductive reactance, and it's measured in the same unit that resistance is measured in a direct current, and it's called ohms. The unit is ohms. What is inductive reactance? Well, it's the inductive reactance is the opposition of the flow of a coil to the flow of alternating current. It tends to slow the current down. And remember, it does it it makes the current flow 90 degrees later than the voltage. Now let's take a look at a circuit here and see if we can make some sense out of it. Here we have a circuit, we'll say with a generator in it, and we have some resistance, some capacitance, and some inductance. And this is a typical circuit. We'll talk more about this later on. Now, as you increase the frequency of the current going through here, you change the rate at which these lines of force expand and contract around this inductance. And the higher the frequency of the current, the more inductive reactance there is. It tends to impede the flow of the current. And because it changes, expands, and collapses the magnetic field much more rapidly. So an increase in frequency will cause an increase in inductive reactance. And also, the more the natural inductance, the more the coils of wire around there will change the inductive reactance. So an increase in inductance itself, and that is how many wires are wrapped around there, how tightly they're wrapped, whether or not you have a core in it, that will change the inductive reactance. And also the frequency of the alternating current changes the inductive reactance. So those are the two things that will change the inductive reactance to a current. Now, there's another thing installed in this current we haven't talked about here. We'll talk about that, and that is capacitance. Now, capacitance is basically two metal plates next to each other with an insulator, or a dielectric it's called, an insulator in between them. And what happens is, remember, this is current that tends to build up, and you build up a charge, and as the current flows, it charges one of these plates. So let's have the current coming through here, charging this plate. Now, if this were direct current, because there's an insulator between the two plates, the current would charge the plate and quit flowing because it couldn't get across this capacitor. But what happens is, with alternating current, the current tends to immediately charge the plate when it gets to a capacitor. It's in a static, all you're doing is putting a static electricity charge on the plate here. So if a static electricity charge on this big plate of metal, and it actually could be aluminum foil, 2 sheets of aluminum foil wrapped around each other with a dielectric or an insulating material between them. But anyway, you're charging this plate first, and if it's direct current, the current will quit flowing immediately. But if it's alternating current, the current tends to reverse in direction, and then what happens, the capacitor gives up its charge right away. And so then the current will flow back this way, charge the capacitor, then it gives up its charge when the current's going back. So this capacitor also tends to impede the flow of current. You can see that when you have direct current, the impedance is absolute. It just completely stops the current going through here. But if the alternating current has a frequency to it, as the frequency increases, this capacitor tends to impede the current less and less because it charges the plate and it gives up its charge. Charges the plate, gives up the charge. And the faster the current changes in frequency and direction, in other words, the faster the frequency of the current, the higher the frequency of the current, the less impedance is imposed by this capacitor here. And by the way, since the capacitor is almost like a short at first, it gives a place for the current to go, what happens is the current is about 90 degrees ahead of the voltage. Now impedance, remember that the current's about 90 degrees behind the voltage, and this is going to become important. So now what determines the amount that a capacitor can store? Well, let's take a look at it. It's directly proportional to the plate area and inversely proportional to the distance between the plates. If you have great big plates, it can store more electricity, and if you move those plates further apart, it can store less. So the closer the plates are together, the more it can store, and the bigger the plates are, the more it can store. Now, there is a maximum working voltage of a capacitor because the dielectric is only so strong. And so if you had too much voltage, it would just jump right across the capacitor and, of course, ruin the capacitor. So what they say is the working voltage of a capacitor should be at least 50% greater than the highest applied voltage you're ever really going to put on it. Otherwise, you could short out the capacitor and go right across it. Now, sometimes in a circuit, including DC circuits, you'll see capacitors installed like this so they go to ground. Now, why do they do that? Well, they do that to smooth out fluctuations in current and voltage. Let's take a look at how it works. Let's assume you have a current going like this and the voltage increases. That voltage will tend to charge this plate of the capacitor, and then when the voltage decreases, that capacitor will give up that charge, and the net result is that it's smoothed out fluctuations in current and voltage. So sometimes a capacitor in a DC circuit is installed to smooth out slight pulsations in current and voltage. Now, just as there are variable resistors, there are variable capacitors, and the FAA is going to ask you on the test, what is the symbol for a variable capacitor? So let's take a look at figure 17 in the back of the book. And in the upper left-hand corner here, you'll see a variable capacitor. It's E. Let's take a real good close look at that. And we get in there and look at that. The symbol for a variable capacitor is the capacitor symbol, the normal capacitor symbol, with a little arrow through it. When you see that arrow on a variable resistor, that arrow is a variable resistor. On a variable capacitor, the arrow stands for a variable capacitor. So that's the symbol for a variable capacitor. Now let's take a look at what happens when you have more than one capacitor in a circuit. You can see right here that we have 2 capacitors in this circuit, and we have them arranged in series. That's one after the other. Now, if you were talking a resistor or inductor, and you had more than one in the circuit and in series, you just add up the resistances or inductances and you'd have it figured out. That's not the way it is for a capacitor. A capacitor is the other way. When you have capacitors in series, they behave like resistors and inductors do when they are in parallel. So when different rated capacitors are connected in series in a circuit, the total capacitance is less than the capacitance of the lowest rated capacitor. Let's take a look at a question they're going to ask you about this on the test. And by the way, you won't have to memorize formulas. They're going to give you formulas, but the question goes like this. You have 3 capacitors in series, 0.02 microfarad, 0.05 microfarad, and 0.10 microfarad. By the way, instead of working in farads, let's keep it in microfarads. All we have to do is keep it the same. Now, they're going to ask you, what is the total capacitance? Well, now, capacitors behave when in series like resistors and inductors do when they are in parallel. So they will give you the formula. You don't even need to memorize the formula, and here it is. What you do is you take the capacitors, and it's 1 over this whole mess, and it's 1 over this capacitor, 1 over that capacitor, and 1 over that capacitor. It's the same formula. They will give you that formula. So it's 1 divided by 0.02. You can use your calculator, and that comes out to 50. 1 divided by 0.05 comes out to 20, and 1 divided by 0.10 comes out to 10. So it's 1 over 50 plus 20 plus 10, that comes out to 1 over 80, and so you use your calculator and figure that out, and it's 0.0125 microfarads. So this is capacitors in series. Now, what happens when you put capacitors in parallel? Well, when you put capacitors in parallel, the total capacitance is equal to the sum of all the capacitors. Now all you have to do is add them up. They'll ask you another question about that. They're going to ask you one that goes a little bit like this. They're going to say you have 3 capacitors in parallel, 0.25 microfarad, 0.03 microfarad, and 0.12 microfarad. What's the total capacitance? Well, this is easy. Even I can do this. You just simply add them up. So the total capacitance is the sum of all of them. You do that with your electronic calculator, and you get 0.40 microfarad. Now, once again, you don't need to memorize these formula. They will give them to you. But for capacitors in parallel, just add them up like that. All right, let's you and I go back and look at our drawing one more time. And we said, just like inductance, capacitance impedes the flow of electricity. What is that called? Well, the term for it is capacitive reactance. And what's it measured in? Just like inductance and impedance, capacitive reactance is measured in ohms. All right, now the combination of resistance, capacitive reactance, and inductive reactance all together is called impedance. And once again, impedance is a combination of resistance, inductive reactance, and capacitive reactance, and all of those things impede the flow of current, or they're in opposition to current in an AC circuit. What is the unit of measure for impedance? You've got it figured out. The answer is ohm. That's correct. The unit for the measure of impedance is an ohm. All right, now, what is the term that describes the combined resistive of forces in an AC circuit? Well, that term is impedance. The combined resistive forces are described as impedance in an AC circuit. Now, on the test, they're going to ask you to figure out the impedance in an AC circuit. And they're going to give you a problem that looks like this. They'll say the inductive reactance in this particular circuit is 10 ohms, the capacitive reactance is 4 ohms, and the resistance is 8 ohms. Now the question is, what is the impedance? As you know, there is a relatively complicated mathematical formula for impedance. But the amazing thing about this question is they give you that formula in the question, and they tell you what all of it means. For instance, they tell you that Z equals impedance, R stands for resistance, X sub L stands for inductive reactance, and X sub C stands for capacitive reactance. And they give you the formula. They say impedance is equal to the square root of this entire expression, which is R squared, that's resistance squared, plus the quantity, and XL's inductive reactance, minus XC, which is capacitive reactance, that quantity squared. And that's the formula, and they give it to you. So all you and I have to do to solve this problem is to fill in the numbers. So let's fill in the numbers. And first of all, the impedance, or Z, is equal to, and it's the square root of the entire expression, resistance squared. And that becomes 8 squared plus, and then that's the quantity. And then the first thing into the quantity, as you remember, was inductive reactance. And inductive reactance was 10. Minus, inside the quantity, is capacitive reactance. And capacitive reactance was 4. And then you close that quantity and square all of that. So now let's take a look at it. Z equals the square root of 8 times 8 is 64, plus 10 minus 4 is 6, and that's going to be squared, plus 6 squared. So continuing down with this, Z equals the square root of 64 plus 6 squared. 6 times 6 is 36. So Z equals the square root of 64 plus 36. add those two together, and Z equals the square root of 100, and you use your electronic calculator, and Z equals 10 ohms. And that's the question they ask you about it, and do not panic. You do not need to memorize that formula. They'll give you the formula. Now here's another question they're going to ask you about a circuit. They'll say a circuit has resistance of 10 ohms, inductive reactance of 20 ohms, and capacitive reactance of 30 ohms. And then they say, how would you describe this particular circuit? Would you describe it as capacitive? And the answer is yes. This is a capacitive circuit because capacitance is predominant. So you would call that a capacitive circuit. Let's you and I take one more look at this circuit we've been looking at for quite a while now. I want to point out there's three things in that circuit. First of all, there's resistance, as you can well see, and also there's capacitance right here. Of course, there's inductance right there. Now let's talk a little bit more about inductive reactance. Let's review it because we talked about it earlier. We said that the higher the frequency in this AC circuit, the more inductive reactance there is. And that's because the magnetic field expands and collapses more rapidly when the frequency of the AC current is higher. We also said that when there is inductive reactance, current lags voltage by 90 degrees. But hold the phone. We also said in capacitive reactance, the current leads the voltage by 90 degrees. And we said with capacitive reactance that when the frequency decreases, we said that you get more capacitive reactance. So these behave opposite of each other. And as you can see right now, there will be a frequency that the AC goes in this circuit in which inductive reactance and capacitive reactance cancel each other out, and it will be as if they were not there. The only thing left in that circuit will be resistance. Now, what do you call that frequency? And the answer is you call the entire circuit and the frequency resonant. When capacitive reactance is equal to inductive reactance, the circuit is said to be resonant. Now here is the answer to the last question we need to cover about AC circuits, and the answer is true power is less than apparent power. Let's talk about what we mean when we say that. Well, if you have inductive reactance or capacitive reactance in an AC circuit, they tend to throw the current out of phase. And that's kind of like having three guys trying to get a car stuck in a mud puddle out of that mud puddle by rocking the car back and forth. Well, if you have capacitive reactance or inductive reactance in the circuit, it's like two of those guys rocking at different times than everybody else. And that means that they won't get as much work done. And that's exactly what happens in an AC circuit when you have either reactive or inductive reactance, or capacitive or inductive reactance, I should say. And the answer is true power then becomes less than apparent power because of either the capacitive or inductive reactance. All right, now let's talk about batteries. And on let's take a look at that, figure 10. In the FA book, they ask you a question about batteries, and they say, what would be the voltage of the total production of this situation right here at A and B at that particular point? What's the voltage? Well, the way you figure it out is we have 1.5 volt batteries. And the important part is, are they connected in series or are they connected in parallel? Now, if you connect batteries in parallel, that means they're connected plus pole to plus pole and minus pole to minus pole. And when you connect them in parallel and they're 1.5 volt batteries, the result will be 1.5 volts. But on the other hand, if you connect batteries in series, you cross the poles. The plus is connected to minus and the plus is connected to minus all along. Then you add up the voltage. Now in this particular case, we have here two pairs of batteries. And notice in these pairs of batteries, left and right pairs, that the plus pole is connected to the minus pole. And over here by the plus poles in the center and the minus poles around the outside of the battery. And again, here we have the plus pole connected to the minus pole. So each pair of batteries gives you 3 volts. Now let's take a look at how the pairs are connected together. And the way the pairs are connected together is that the plus pole is connected to the plus pole, and the minus poles are connected to the minus poles as far as the pairs of batteries are concerned. So you have 3 volts on this side, 3 volts on that side, and since they're connected parallel, it's still 3 volts, just more capacity. And so now you'll find that if you put a voltmeter right across A to B, that you'd have 3 volts. And that's the question they ask you about on the FA written exam. So in this case, you would read 3 volts. Now, let's talk about aircraft batteries called storage batteries inside an aircraft. This is an example of a lead-acid storage battery inside an aircraft. And they want to ask you, and they will ask you, a few questions on the FAA written exam about these batteries. Let's take a look at it. First of all, how are batteries rated? Well, they're rated according to voltage and ampere-hour capacity. How many amps can they put out for what period of time? And that's called ampere-hour capacity. Now, the state of charge determines the current that will flow through a battery while it's being charged in a constant voltage source. Now let me explain that just a little bit. And a constant voltage source is like a charger or a generator or an alternator in the aircraft. And the generator or alternator puts out a constant voltage, we'll say 14 volts. And when the battery is extremely low, a lot of current flows into the battery. But when it's charged, very little current flows into the battery. So it's the state of charge that determines the current which will flow through a battery while being charged by a constant voltage source. By the way, the other way you could charge a battery, and you do this very often on certain batteries, is a constant current source of charging a battery. We'll talk more about that later on. Now let's talk about some specifics they ask you about lead-acid batteries. First of all, they want you to know that a sulfuric acid that's used as an electrolyte in there has a much lower freezing point than water. And what that tells you is a fully charged lead-acid battery will not freeze until extremely low temperatures are reached, because most of the acids in solution, and sulfuric acid has a much lower freezing point than water. Another question they ask you about is a hydrometer reading. And what you do is you can measure the charge of a lead-acid battery by measuring the specific gravity of the electrolyte with a hydrometer. And they want you to know that a hydrometer reading does not require a temperature correction at 80 degrees Fahrenheit. And that's generally true because anywhere between 70 and 90 degrees Fahrenheit, you do not have to correct the hydrometer reading for temperature. So 80 degrees Fahrenheit is a good temperature. Now let's assume you're working with a lead-acid battery and maybe you tilt it or something and you spill the electrolyte solution all around an aircraft. Well, the owner of the aircraft is going to think that is a very bad thing. They're going to ask you how you did it. But the question is, what are you going to do to get out of this mess? And what you want to do is neutralize it with an alkali. The electrolyte is very acid. You want to neutralize it with an alkali, so you'd use something like sodium bicarbonate, because that's an alkali. So you'd apply sodium bicarbonate, and then of course you wouldn't want to leave that lying around the aircraft, so then you'd rinse it with water. The best thing is, don't spill the electrolyte. The owner will not like it. Okay, now let's take a look at another problem with lead-acid batteries. And sometimes you have a sediment buildup at the bottom of a lead-acid battery. It builds up under the plates here in a cell container. And if that sediment builds up enough, it can contact these plates and cause a short circuit. So to prevent sediment buildup from contacting the plates and causing a short circuit, they provide lead-acid batteries with a space underneath the plates to hold that sediment buildup so it doesn't contact the plates. Now let's take a look at nickel-cadmium batteries, or NiCad batteries. As you know, NiCad batteries generally are used in turbine aircraft because they have very little internal resistance and they can put out a tremendous amount of electricity in a short period of time. What is the electrolyte used in a nickel-cadmium battery? It's potassium hydroxide, and you need to remember that on the test. Now, the level of electrolyte in a NiCad battery is low sometimes. Let's take a look at when the level is low in a NiCad battery, and the answer is when it's discharged. The level is lowest in a NiCad battery when it's discharged. By the way, you might be interested in what we're looking at here behind us. This is a NiCad cell, one cell out of a battery that is being strapped off to short it out to make sure that it's completely discharged before it's charged. Okay, now, remember we said earlier the level in a NiCad battery is lowest when it's discharged. So what would happen if you add water to a NiCad battery when it's not fully charged? Well, the answer is you'd have spewing, excessive spewing, the FAA says, if you add water to a NiCad battery when it's not fully charged, because the level automatically comes up when it's charged and then you could spew it out. Because at the end of a charging period, a NiCad battery tends to put out some gas. Nickel-cadmium batteries or NiCad batteries, which are stored for a long period of time, will also show a low fluid level, and you need to know that. Now, here's a question I do not like on the FAA written exam. They ask you, how do you determine the state of charge of an NiCad battery? And the answer, the only one that can possibly be a correct answer, is that the state of charge of an NiCad battery can be determined by a measured discharge. Now what they're talking about is you discharge the battery at a specified rate and measure its ampere hour capacity, then recharge it. Now that might be a way to tell the condition of the cells of the battery, but I don't think it's a very good way to determine the state of charge. Doesn't matter what I think. When you look at the FAA question and you go back and look at the FAA sources of information, this is the only one that's the correct answer. So this is the correct answer regardless of what I think of it on the FAA written exam. It doesn't matter what I think. I guess it matters what the FAA thinks. So the state of charge of a NiCad battery, according to the FAA on the test, can be determined by a measured discharge. All right, now, should you ever service NiCad and lead-acid batteries together in the same service area? And the answer is no, you should not, because it can result in contamination of both types of batteries because the fumes are not compatible with each other. Now let's talk about charging batteries and the methods you can use to charge batteries. Charging batteries is a good idea. If you couldn't charge a battery, you could use them only once. That's not such a good idea. Let's take a look at the methods. One method you could use to charge a battery is the constant voltage method. Now the constant voltage method is what you're using in the air because a generator puts out a constant voltage, and what happens is the rate of charge is very rapid when the battery is very discharged, and the rate changes and gets less as the battery becomes charged. So the constant voltage method gives you a constant voltage, but the current or the rate of charging varies. Now the advantage of the constant voltage method is that you get a very rapid charging rate, particularly when the battery is very discharged. However, the disadvantage is if you have a NiCad battery, that very high charging rate could actually cause the battery to overheat. So that's both the advantage and disadvantage of the constant voltage method because you're not really controlling the rate that you're charging the battery. Now let's take a look at the other method, the constant current method, and it does exactly that. It does control the current going into the battery, and it does that by varying the voltage. So you have a constant current going into the battery. The advantage is that you do have that controlled charging rate. The disadvantage is that it takes longer when you control the rate, and generally you'll have a lower rate of charge. Now, if you're charging multiple batteries at the same time, you could use the constant voltage method. To use the constant voltage method, the batteries must be connected in parallel, and they can even be of different capacities, but they must be of the same voltage because you're applying a certain voltage to the batteries, and you therefore want the batteries to all be of the same voltage. On the other hand, if the batteries are of different voltages, you could use the constant current method. Then the batteries are connected in series, and they can be of different voltages, but they must be of the same capacity. So if you have them all of the same voltage, you'd probably want to use the constant voltage method. If they are of different voltages, then you could use the constant current method. But if they're of the same voltage and capacity, you can use either method of these two, and it's your choice. Let's take a look at the next question. When do NiCad batteries tend to emit gas? Well, the cells of NiCad batteries emit gas only towards the end of the charging cycle. We talked about that earlier. Now on the test, they're going to ask you what determines the cell voltage of a fully charged 19-cell nickel-cadmium battery. And the answer is temperature and the method used for charging determine the cell voltage. So it can vary. Cell voltage normally varies from about 1.45 volts to 1.58 volts, and that's determined by the method for charging and the temperature. Now, one thing about NiCad batteries is they can develop a condition that's really bad called thermal runaway. And let's take a look at how it works. Here's an example, by the way, of thermal runaway. It's a cell that's had thermal runaway. This is just a very mild case of the result of the damage from thermal runaway. It can get a lot worse than this. So let's take a look at it. First of all, NiCad batteries tend to heat up when current moves either into them or out of them. So let's assume that you've really discharged the NiCad battery. Say you had a difficult engine start, and now you're charging that battery back up. Well, it'll tend to heat up the battery when you charge it back up. Now, NiCad batteries have low internal resistance, so it allows a very high rate of charging current. And that, of course, heats up the battery further as you charge it. So you discharge it, it heats up the battery. You charge it, it heats up the battery. Now, high temperatures in a NiCad battery cause the separating material inside the cells to break down, and that even further reduces the internal resistance, and that allows even more current flow, which causes an even higher heat inside the cell and more separator material to break down. So that cycle is called thermal runaway. So what contributes to thermal runaway? Well, the low internal resistance of the battery is one factor, and of course the resistance gets even lower when you have high cell temperatures. And finally, the charging system in the aircraft makes a difference. First of all, it discharges very quickly, and that tends to heat it up and start this cycle, but it also charges very quickly. And one of the reasons it charges very quickly is that we have generators in aircraft that put out a constant voltage. That's called a constant potential charging system. And what that means is when the battery is very discharged, it charges up very rapidly, and that tends to heat the battery even further. So as you can guess, thermal runaway is really a bad thing. It can cause the battery to sever the control cables, or can even cause the battery to fall through the floor of the aircraft. So what's the solution to all this? Disconnect the battery so that these things are no longer in play. Let's assume that you find heat or burn marks on the hardware of a battery. What's that an indication of? Well, it's an indication of improperly torqued cell link connections, and it means you have had some arcing there. What is the most probable cause of an excessive amount of potassium carbonate formation on a battery? And the answer is battery overcharging will cause an excessive amount of potassium carbonate formation. All right, and nickel-cadmium battery cases and drain surfaces which have been affected by electrolyte should be neutralized. What should you neutralize them with? And the answer is a solution of boric acid. And that is everything they ask you about AC current and batteries on the written exam. Now let's you and I do something really fun. Let's talk about troubleshooting in electrical diagrams for electrical circuits. And here on Figure 8 in the FA book is a good example of an electrical circuit in the diagram. Now the question I want to talk about here is how do you use an ohm meter to correctly test a resistance? And what you do is you put the ohm meter parallel to the resistance. Now what the ohm meter does is it sends a little current through the resistance and checks the resistance by doing that. By the way, we have a break in this resistor, so that doesn't factor in at all. And we're sending a current through these two resistors. In order to do that, you must have at least one end of the resistors disconnected. In this particular case, we have the switch open, and therefore we can send a current around. Then the ohm meter measures how the current goes and measures the resistance. Now, if you did not have an open circuit, you would have a voltage going through here and a current going through here, and that, of course, mess up your reading. So the correct way to use an ohm meter is to put it parallel to the resistors you want to check and have at least one end of the circuit open, and that's what we have right there. Let's you and I do another one. And to do that, let's take a look at Figure 9. And son of a gun, here is Figure 9. They're going to ask you a question about this, but let's talk about the correct way to connect an ammeter. And here we have an ammeter correctly connected in here. The ammeter should actually be in series with the circuit at the point where you want to measure the amperage, and actually what you have is the current actually flows through the ammeter, and that's the case here. You've got the current flowing through the ammeter. Now what you want to avoid when you're using an ammeter to test a circuit is you want to avoid creating an unintended second path for the current to flow, and that's what's been done here. You wouldn't be testing anything here because now you're creating a second path for the current, and that's certainly not desirable. So this ammeter is incorrectly installed because it's basically creating a second path for the current. Actually, could even be considered a short here, and that's a bad deal. You want the ammeter in series with the circuit, so this ammeter is correctly installed, this ammeter is incorrectly installed. Now let's talk about how to connect a voltmeter to test the circuit. Well, in a voltmeter, you want it parallel to the circuit that you're testing. In this particular case, we're probably testing the voltage drop-off across this lamp. So we have the voltmeter parallel to the lamp, and we can test the voltage drop-off. Now, one of the things you want to be careful of is the polarity of the voltmeter. Here you have the minus side of the voltmeter. Here's the plus side. You want to make sure each of those goes to the right side. So the plus should come down here and come to the plus end of the battery, which it does. And the minus should come over here and come to the minus end of the battery, which it does. Now, we have another voltmeter in this drawing here, and it's improperly installed. And the reason it's improperly installed is the plus goes to the minus side of the battery, and the minus goes to the plus side of the battery, and that's improperly installed. So they're going to ask you a question about Figure 6 here in the test, and the question is, how many of these meters are correctly installed and how many are incorrectly installed? And the answer is, one ammeter is incorrectly installed, one ammeter is correctly installed, one voltmeter is incorrectly installed, and one voltmeter is correctly installed. So there's two of each there. So you guys have got that figured out. Now let's you and I take a look at figure 20 and see if we can figure out the question they ask us about this. And they say, all right, super mechanic, let's assume you're troubleshooting this open circuit. Now the reason it's an open circuit is there's a break in a resistor right here. You're troubleshooting it, you've installed the voltmeter like so. Now the question they're going to ask you is, will you get an accurate reading of the battery voltage with the voltmeter installed the way it is? And the answer is yes, you will. This is okay. But you say, wait a minute, hold the phone. Won't there be a voltage drop-off across the resistance of this lamp? And the answer is yes. If there were a current flowing in here, there would be a voltage drop-off across that resistance, the resistance of that lamp. But since there is no current flowing, then there is no voltage drop-off, and you will get a true measure of the voltage of the battery with no current flowing. Had there been a current flowing, then you would have had a voltage drop-off and not had a true measure of the battery. I consider that kind of a tricky question. All right, let's take a look at one ammeter question. And here it is. An ammeter shows a full charge rate, and this is in the aircraft. We're talking about an ammeter in the aircraft. And the battery remains discharged. What's the problem? Well, the most likely cause is an internally shorted battery. The battery itself is shorted out, and no matter how much you charge it, it stays discharged. There's nothing you can do about it. So that's one of the things to check for. If an ammeter in an aircraft shows a full charge rate, but the battery remains discharged, the likely cause is an internally shorted battery. Now here is the fun part. Here's figure 18 out of the FA book. It is, as you figured out, an electrical diagram. And we're going to have some fun with these. We're going to make them easy, so don't panic. Now whenever I look at an electrical diagram like this one, the first thing I always try and figure out is where is the electricity coming from and where is it going to? Well, where it's coming from is some kind of power source. Here's a bus up here. It might have 24 or 28 volts, and where it's going to is ground. So what you do is figure out where the grounds are. Here's a ground here, here's a ground here, here's a ground here, and here we've figured out a relatively circuitous path to the ground like so. So what you're trying to do is figure out the path of the electricity from the power source to the ground. So the first thing to do when you look at these drawings is identify the power source and identify the grounds, and that way you know where you might be going. Now let's take a look at a question they're going to ask you about this, and what you need to know to answer this question is this. In this case, figure 18, the control valve switch must be placed in the neutral position when the landing gears are down to prevent the warning horn from sounding when the throttles are closed. And what they're saying here is even though you have the landing gears down, the warning horn will still sound when the throttles are closed unless you have the control valve in the neutral position. Let you and I prove it. Let's start at the ground and trace the current back to the source. And here we are in the ground, in the lower left-hand corner, and we have wire 14. And we have the left gear switch, and the gear is down, so we have this switch closed because this tells you when the gear is down, that switch is closed. And so now we have from the ground through wire 14, the left gear switch being down, and now we have wire 3 here, and the right gear switch is down. We've still got a continuous circuit here, a continuous path. And now, notice that if the control switch is in neutral, it would be over in this position. But if the control switch is not in neutral, other than neutral, it would be in this position. Let's see what happens if the control switch is not in neutral. Then you would have a path for the current to wire 10. Now let's go beyond wire 10 to wire 5. And now, when the throttles are closed, these switches are closed, and now you have a path through the throttle switches to wire 6, to the warning horn, and then through the warning horn, which will now sound all the way back up to the current source. So you see, let's take a look at this switch again. When this switch is not in neutral, the warning horn will sound even though the landing gears are down. And you have just answered the first question about this, and all we had to do was trace our way through it. By the way, it is a good idea if you've got a book that you can mark in to use the yellow pen and do exactly what we did to figure out where everything is going. Now, if the control valve switch were not in neutral position, that is the path the current would take. Let's take a look at another example. And we look at figure 18, and the question is, what you need to know is, when the landing gears are up and the throttles are retarded, The warning horn will not sound if you had an open or a break in wire number 4. Well, let's take a look at it. We'll start over here in the lower left-hand corner with the ground. And of course, the ground is connected to wire 14, which is connected to the left gear switch. When the gear is in the up position, the switch will be over here. Then you're connected to wire 4. Then you have the throttle switches. And when the throttles are closed, these switches are closed also. So you'll go through the throttle switch to wire 6. Then you'll, of course, go through the warning horn. Then the warning horn is connected back to the power source, and you can see the warning horn would sound. So if you have a break in wire 4, all of that's not going to happen. So you can see the warning horn will not sound even when the gears are up if you have a break in wire 4. Now they're going to give you some other options. They'll say, well, how about if you had a break in wire 2? Well, if you look at this diagram, wire 2 has to do with the red light warning circuit. So that doesn't have anything to do with the warning horn. And they say, well, how about wire 9? Well, wire 9 has to do with the green light circuit. So that doesn't have anything to do with it. And how about wire 10? Well, wire 10 has to do with the control valve circuit, and that doesn't have anything to do with it. So the correct answer is the horn will not sound if you have a break in wire 4. Now let's take a look at figure 19 and take a look at some questions we're going to ask about figure 19. Here's an answer to one of the questions. Let's follow it through and see if we can make some sense out of it. The answer is the condition which will provide a ground for the warning horn through both gear switches when the throttles are closed is only the condition that when the left gear is up and the right gear is down. Now there are other ways for the warning horn to sound, but this is the only way that it uses both gear switches. Let's take a look at it. First of all, we'll start with the ground in the lower left-hand corner of the drawing, and then we have the right gear down. That was the condition, and this arrow tells you the right gear is down when the switch is over in this position. And then we go along wire 5, and the left gear had to be up for this condition, if you remember. Now, this drawing is shown with the left gear down, but put the left gear up, and now you have a contact through here. And then we go along wire 12, and these are the throttle switches. When the throttles are closed, we have a route to a wire 11, and the warning horn will sound. And then you go through wire 10, let's complete the circuit, and back to your 28-volt DC source. So the only route that provides routing through both gear switches for the warning horn to sound is when you have the left gear up and the right gear down. Now, if you have other situations with one gear up, you'll still have the warning horn sound. It'll just provide a different route for it. And that's the way they're going to ask you about this on the test. Now, here's another question they're going to ask you on the test. It's very similar. They'll say, take a look at figure 19. And what would happen if you had that same situation? You had the right gear down, the left gear up. What would happen if you had an open in wire 5? Well, if you had an open here in wire 5, you've broken the circuit, and the warning horn will not sound when the throttles are retarded. So if you have an open in that circuit, obviously it's not going to work. So if you had that same situation, and that same situation is the right gear down, a left gear up, had an open in wire 5, the warning horn's not going to work properly. Now, figure 19 is pretty complicated, so therefore the FAA loves to ask you questions about it. So they're going to ask you yet another question about figure 19. Now, here is the question. When the landing gears are up and the throttles are retarded, the warning horn will not sound if an open occurs in wire number 6. Now, the reason for that is only the right gear switch sounds a warning horn when both gears are up. Let's take a look at it. First of all, when the right gear is up, this switch is over in this position. Now, notice we have wire 5 here, and when this right gear switch moves to this position, it disconnects wire 5. So wire 5 is not connected on the left end. Remember that. We're going to talk about that later on. Okay, now we do have a path from the ground through the right gear switch over here to wire 6. So we'll continue across on wire 6, and we go up through to wire 12, and then we go through the throttle switches. You can see that sounds the warning horn by going, of course, the warning horn is connected by 10 to the power source there. So you can see that if you do have wire 6 with a continuous connection in it, that the warning gear will sound, or the horn will sound when the right gear is up. And the left gear is also up. Remember, the left-hand side of wire 5 is not connected. Let's go over here and see what would happen. And even though the left gear switch is up, it's only connected to wire 5 through wire 12. It's not grounded. So the left gear, when both wheels are up, does not sound the horn. It's the right gear switch that sounds the horn. And if the wire 6 is disconnected, then neither one would sound the horn. So what they want you to know is, in this particular drawing, if you have an open in wire 6 with both gears up, the horn won't work properly. And that's the answer to that question. Now let's take a look at figure 15. And the thing you need to know about figure 15 is very simple. What does wire number 7 do? And the answer is, it's used to complete the push-to-test circuit. Well, let's take a look at what we're talking about here. First of all, we have the bus on the left-hand side. Wire 7 will go around here. We'll trace this in more detail in just a second. And then you get over here on the right-hand side, a couple push-to-test switches and lights, and then finally a ground. So what we need to do is complete the circuit from the power source to the ground. All right, let's start over at the power source. And here we have a bus with a 5-amp circuit breaker and then wire 7. So you can see wire 7 is going to be instrumental here. It comes right from the bus. And then we go through wire 18, and then here's a light with a push to test, and when you push on it, you complete this circuit here, and then it goes all the way over to ground. And you can do the same thing through wire 17 for this light. Push on it, and you complete a circuit all the way to ground. So you can see that wire 7 does complete the push-to-test circuit. Wire 8 is the normal source for providing those lights as a warning. So wire 8 would be the warning power source for those lights, but wire 7 is the push-to-test power source for those lights. And that is a simple one. Let's complicate things up by taking a look at another question in figure 15. This time they ask you to know this. With the landing gear retracted, the red indicator light will not come on if an open occurs in wire 19. Well, we've already kind of referred to that. Let's take a look at it. The landing gear is retracted, so we'll start off with the power source over here. And we'll take a look at wire 19. And if you have the landing gear retracted, this switch is in the up position. And so now you have this switch in the up position, and we go through wire 8. And wire 8, as we said earlier, will light this red light because it's connected right to the red light, and then that goes to ground. So you can see that wire 8 is our path. Now let's go back and make sure that we've answered the question. And what you need to know is if there is an open in wire 19, none of that will happen. And they ask you that on the test. So what you would do is troubleshoot and look for an open in wire 19. And then if there is an open in wire 19, the red light would not illuminate. Those are typical questions they're going to ask you about this. Let's take a look at one more question on figure 15. And what you need to know in this case is when the landing gear is down, the green light will not come on if an open occurs in wire 6. Well, let's take a look at the circuit when the landing gear is down. First of all, we'll start over here at the bus, and we'll go through this 5-amp circuit breaker. We'll go down here to wire 6, and the nose gear is down, so the switch is in this position. That's nose gear down switch, and that makes contact with wire 5. The left gear is down, and so we have that switch closed. And number 4, wire 4, and the right gear is down. That switch is closed. And then we go through wire 3, and of course the green light will now operate because we have a connection all the way to ground. Now, the question is, what happens if wire 6 has an open in it? Well, if wire 6 has an open in it, none of this will happen because the current will get broken right at the start of its travel. And you can see that if we had an open in wire 6, then the green light would not illuminate. Okay, you guys are doing just absolutely fantastic at this. Let's take a look at fuel system circuits. And to do that, let's you and I take a look at figure 16. Now, there are some things that we need to explain about figure 16. First of all, what you do on all of these drawings, you find your power source. Your power source is up at the top, and then you go to some grounds. Now, we need to talk about a couple concepts. We need to talk about relays, and we need to talk about solenoids. So to talk about relays, let's start off on the left-hand side and follow the normal power source. This is what happens when things are normal. Now, first of all, you have power at this bus. It's a 24-volt bus. You have power at this bus. Here you have a circuit breaker. And in the normal position, everything goes right straight down. You see this switch is a switch over here, but it dead ends at this terminal 4. And so in the normal position, everything goes right straight down this direction. Now, this is the concept of a relay, and let's take a look at it for just a second here. First of all, notice that we've got a ground right here. And what happens is, if there were power to this relay, this switch, this whole assembly would move over. A relay is an electromagnetically controlled switch. And if you put power on the electromagnet, which is what you have right here, an electromagnet, a coil of wire, then you're going to pull both of these switches over. Now, we have this drawing shown with everything without power on it. Here's the way switches look when they don't have power on it. Now, this LTS relay then, when it has power on it, pulls over switches 5 and 6 to this position. They are shown in a position without power on it, so switch 5 would open and switch 6 would close. But as it is right now, there is no power to the LTS relay when things are normal, so switch 5 is closed, switch 7 is closed, switch 9 is closed. None of these relays have power on them. Now let's get down here and talk about the concept of a solenoid. A solenoid is very much like a relay. It's an electromagnetic switch controlled with an electromagnet, but a solenoid has the core move in and out of it. It's got an iron core that can move in and out, and you can use that core to move big things like valves. Now, so this could be, for instance, operating the crossfeed valve. Solenoids, as a general rule, are bigger than relays, and they can operate other things like valves in addition to just little electrical switches. Now, here we have a solenoid. When this solenoid has power on it, what happens is that the whole thing moves over to the right, and switch 12 becomes activated. It changes its position over to this position, and switch 11 becomes activated and moves over to this position. And that opens switch 11 and closes switch 12 in this particular case when this solenoid is activated. But remember earlier I said that this drawing now is shown without any power on it. So without any power on it, we have a path right down here, through switch 11, which is not activated, and we'll go right along this wire up here, and then we'll go back up towards the top of the drawing. And we have now, finally, one relay that has power to it, and that is the PCC relay. And the PCC relay then would open this switch so that there would be no way that power could get on to turn on this light, which is the fuel pressure crossfeed valve open light. And so when things are normal, this PCC relay is activated. Now let's take a look at what other relays might be activated. And let's zoom away and take a bigger look at this drawing, see where our paths are. What we did was we just now went on a path from the bus through all of these relays, and none of them have power on them, so we have a straight shot through these relays, and the solenoid doesn't have power on it, so we're going through this position right here on switch 11, right here to operate the PCC relay, and that will open this switch right here. Now on the other side, we have the 24-volt bus up here, and we'll have power going down this direction like so. And let's take a look at where that power goes when we get down here. And first of all, we have a relay that has no power on it. That's a crossfeed relay, and I'll show you later that only activates when you have crossfeed for the tank crossfeed set on. We don't have it, so there's no power on it, so that switch will be closed. This solenoid has no power on it, so the solenoid only gets power on it, by the way, when the tank crossfeed switch is activated. And so we have no power here, so we're going to go through and we're going to have these switches in a no power position, which is where they are right now. And we'll go through this switch, and we'll go across here, and we'll come up here, and let's take a look and see if we have power on any relay. And son of a gun, we do. We have power on this relay right here, which is the TCC relay. So we do have power on that TCC relay, and that means this valve right here, this switch would open, and the fuel tank crossfeed valve light would not come on. So if you are in the normal situation then that we just described, the PCC and the TCC relays would be energized. And what we're talking about here is they would have electrical power to them. When we're talking about a relay being energized, it has electrical power to it. Now, when it's not energized, the spring holds the relay in the opposite position. When there is electrical power to it, the electromagnet pulls the relay over like so. So you can see that these are the two routes of current. Let's take a look over here on the left-hand side. We have the crossfeed relay right here, and this is the fuel cross-feed relay, and that only gets activated when the switch up here at the top, and here's the switch up here at the top, is in the cross-feed position. If it's in a cross-feed position, then power comes over here. So you can see that this cross-feed relay, when it's on, then would pull 9 and 10 over, and it would also activate the far right-hand side down here and pull 17 and 18 over. And it would also then activate at the same time 19 and 20. Since that relay is not activated, that's why we don't have to worry about the path changing here. So what we have activated when things are normal are the PCC and TCC relays. Then they're energized. All right, now let's take a look and see what would happen if you move the fuel selector switch to the right-hand tank. Okay, we'll start up here at the bus, and here we are up the bus up here like so. And let's get in a little tighter and take a look at how we're going to move this to the right-hand tank. And here we are. We'll move this switch to the right-hand tank. What it would mean is you start at the bus, you go through here, now you have a connection to this position right here. And that means the power is going to take this direction right here. So let's take a look and see where it goes. And when that happens, the RTS relay is energized. Now, the LTS relay is not energized, so the current is coming from the bus right straight down here. But when the RTS relay is energized, switch 7 is moved to the left, and that's an open. And now switch 8 is closed, and now we have a path that goes like this for the current. Now, since we have a path that goes like this for the current, we hit terminal A here, and that means this whole solenoid is activated, and switch 12 will close and switch 11 will open. Now, since switch 12 is closed, we're going to go this route back up through terminal C, and the PCO relay is energized. And when the PCO relay is energized, switch 13 is closed, and power comes from the bus right through here, and then the fuel pressure crossfeed valve light would be open in that particular case. All right, now let's take a look at where else the current is going in this particular case. And we'll start up again at the upper right-hand corner. And when you get in the upper right-hand corner, taking a look at that, there we are. We're at the upper right-hand corner. And we have the 5-amp circuit breaker. The power comes down here. And remember, the fuel crossfeed relay is not energized. So we're going to write the same circuit to figure through switch 20 here. Everything's just the same as it was. We're going to go back up here through terminal D, and we find out that TCC is still energized. So now the question is, what relays are energized when you switch to the right-hand tank? Well, we said TCC is energized. Let's take a look at what else is energized. And if you take a quick look at it, RTS, let's zoom in a little tighter and make sure we're looking at RTS. RTS becomes energized. And then also PCO becomes energized. PCO was way back up here, and PCO becomes energized. So you see, if you switch the right-hand tank, the relays RTS, PCO, and TCC become energized, and they have operated. Well, wait a minute. I can hear you asking right now. You want to know what happens if you switch to the left-hand position. All right, I could tell you we're going to do that, so let's switch to the left-hand position. We'll start out at the bus, we'll come through this switch, and we'll take a close look here at the valve and make sure that we're in the left-hand position with it. And if you zoom in tight, you see now we have the left-hand tank right here. So now we're at the left-hand tank. Now if you go on down, you can see that we have energized some relay here, and we have energized the LTS relay. When you've energized the LTS relay, switch 5 moves over and becomes open, switch 6 becomes closed. So power, which comes from the top, now goes through switch 6, and it goes to A. Now, this solenoid is now activated when when we're in terminal A, and switch 12 is activated, switch 11 is activated. And then we're going to go take power up back through C here, and we're going to go up and activate the PCO relay, and that will activate switch 13. All right, now let's take a look again what happens on the other side of the drawing when we put power in on the other side of the drawing, and it's all the same every time unless we operate that tank crossfeed switch. But here we have power coming down from the 5-amp circuit breaker, and once again it goes through the right-hand side of this solenoid back up, and once again, since we haven't operated that tank crossfeed, we're still only going to have one relay activated, and the relay activated is this TCC relay, which activates switch 16. Now, the question they're going to ask you about this is, let's assume you turn on power with the left fuel tank selected. which switches will be energized or moved. So let's take a real quick look at it and start over and review it and see which switches will move. First of all, you're going to activate the LTS relay, and that will automatically activate both switches 5 and 6. So we know switches 5 and 6 will activate, and they activate as a pair. If you turn on the LTS relay or energize it, you get both switches to activate. Now come down here and you see that we've turned on to terminal 12. We've come to terminal 12, activating this solenoid, and that automatically activates switches 11 and 12. And they act as a pair also. All right, now let's go back up here and see what happens. We've now energized the PCO relay, and all of a sudden that automatically means switch 13 is activated. All right, now we're going to have one other relay that's activated, and that's this relay right here, which is the TCC relay, and switch 16 becomes activated. And there is one more switch that we need to talk about that does momentarily become activated, and that's switch 15. And let's see if you and I can trace out how in the world switch 15 momentarily becomes activated. And we're including this in the answer because all of the correct answers on the FA test refer to switch 15 as being activated. How can we say it would be activated? Well, let's go back up at the top and turn on the power. And what we have selected the right-hand tank, but at the very moment you turn on the power, what's going to happen is these relays have not been activated yet. So there is a path of current right straight down through terminal 11. The solenoid's not activated yet because you just turned on power at that instant, and you're just for a second going to get a flicker of power over here to the PCC relay, and that will activate switch 15. Now, as soon as power comes on, all those relays will activate, and that'll cut off power to switch 15. But for just an instant, we're going to have power to switch 15, and that will operate also, and that's why we include 15 in the answer. Now, the real reason we include 15 in the answer is the FAA has it in all of their answers that make sense, so we know they expected that switch to operate for just a split second there. So the answer to this question is, if you select the fuel tank position of the left-hand position, turn on the power, switches 5 and 6, they operate together, 11 and 12, they operate together, 13, 16, and 15 will all become moved or energized or activated, and 15 is only activated very briefly. Now let's take another look at figure 16, and let's take a look at another question they're going to ask you here on figure 16. And the question they're going to ask you says, if the PCO relay in figure 12 failed to operate when the left-hand tank was selected, what would happen? And the answer is the fuel pressure crossfeed valve open light will not illuminate. Well, let's take a look at the fuel pressure crossfeed valve open light, and it's right here. It's fuel pressure crossfeed valve open, and they're saying if what relay failed to activate? Well, the answer is if the PCO relay failed to activate. Well, here is the PCO relay, and what we're saying is if this relay failed to activate, switch 13 wouldn't work and this light would not come on. And that's the question they ask you about that. What would happen if you did switch to this condition and the PCO relay didn't activate? That means that light would not come open because switch 13 wouldn't come over to provide a path for the current. All right, let's take a look at another question they're going to ask you about figure 16. And here's the answer to this question. That is that TCO relay will operate if 24 volts DC is applied to the bus and the tank selector is this time in the crossfeed position. That's when the TCO relay will operate. Well, let's take a look at it. We start up here at the power again, and this time we're going to send power over here to the crossfeed position. And let's go down right here and take a look at what happens when you're in a crossfeed position. And first of all, in the crossfeed position, the FCF relay will operate. All right, now what happens when the FCF relay operates is that these switches move over, and you have an open on 9 and a closed on 10. So power is coming right straight down from the top, going through 10, going through A, and now this solenoid will activate, switch 12 will close, switch 11 will open, and power will go up here, and we'll get to the PCO relay, and the PCO relay will operate switch 13. But wait, there's more. So let's go back down to the bottom in the lower left-hand corner and take a look at what more there is, because we are also operating the FCF relay, and it's operating switches 9, and we're also operating switch is 10, and that same relay comes all the way over here. This same relay comes all the way over here and activates switch 17 and switch 18. Okay, now, when we've got we're asking about, remember, we're asking about the TCO relay, so now we're providing a path. These switches have moved over, 17 is closed, 18 is open, and we're providing a path to A. This solenoid becomes activated, moves over, and now we have A closed, that switch is closed, and now we come up here, and son of a gun, the TCO relay is activated. It closes this relay, or this switch, and now we have that light operating. And so through all of that complicated route, the TCO relay was activated because we have crossfeed on. And if you go back in the lower left-hand corner, you can find out why that happened to you. And the reason that happened is when you turn crossfeed on, the FCF relay is activated, and that pulls this whole bar of switches all the way across and activated that particular relay at the top, which was the TCO relay. See? Nothing to it. All right, now let's cover just a last couple items about electricity. And before we do that, before we take off and do these new items, I want to point out to you that the way that I think is easiest to answer all these questions is when they ask you on the test, get a pencil and paper and make a chart and say, what would happen if the power was normal? And you make a list of all the relays and say, would they be activated? For instance, if the power is normal, the LTS relay would be activated. And the answer is no, it would not. That was supposed to be a question. And if the power is normal, would the RTS relay be activated? And the answer is no, it would not. How about the FCF relay and so on, all the way down through? How about when power is on the right tank? Well, would the LTS be activated? No, because L stands for left. How about RTS? Yes, because R stands for right. And you begin to get a pattern here. And so left, right, fuel cross-feed and all of that, you'll begin to understand what all these relays mean. So when you get on the test and they ask you this question, by the way, I'd put this question off to last because it's going to take a long time to answer. And I would get the easy ones done first because they're all weighted the same. But in any event, I would make up this table, and we've got the table in the book so you can practice on it and see what relays are going to operate when, and then you can answer the questions. Now here is an electric motor that could occasionally overheat. Now, what is the desirable thing when an electric motor overheats? Well, the desirable thing is this. You have a thermal switch in the electric motor that breaks the circuit and prevents a fire. That's the desirable thing, and that's what they tell you will happen on the test, that when an electric motor malfunctions and overheats, it can incorporate a thermal switch that will break the circuit. Now that's logical, and speaking of logical, let's talk about a new subject, and that is called logic gates. Logic gates are circuits that you can use to pass on information, and they're based on the idea of binary mathematics. Binary mathematics means you can have either 1 or a 0. Something has either got a charge on it or no charge on it. If it has a charge on it, it's a 1. If there's no charge on it, it's a 0. And you can use that system to pass on information. And this is a logic gate, and here's the way it would work. First of all, you have an input, and each input can have either a charge on it or no charge on it. And if a certain condition satisfies the requirements of the circuit, then information can be passed out here. If this is true, then I'm going to turn the charge on here and put an output here. This particular logic gate we're showing right here is what is known as an AND gate. Because what happens is, in order for there to be an output charge out here on an AND gate, in this particular case, what you have to have is all three of these be true. There must be a charge here, and here, and here. And if all three of those are true in this particular case, then you would have an output here, and that is what is known as an AND gate. So all three of them have to be true. Now they're going to ask you a question about this on the test, and the question they're going to ask you about it on the test is, if you had this logic gate depicted and you had an output of 0, what would be the case? How would that get to be that way? And the answer is, in order for there to be a 0 output, you must have one of these not have a charge on it. Because in order for there to be an output, you have to have all three have a charge on them. That's called an AND gate. Now let's take a look at what is known as an OR gate. And an OR gate, you might notice, has the shape of a boat. And if you have any trouble remembering that this is an OR gate, remember that boats have oars. and I am so sorry. That's the way it works. You're going to remember it now for the rest of your life. Now, here's a case of an OR gate, and what we're saying in an OR gate is if any one of these inputs has a charge on it, then there will be a charge out here, there will be an output here. And once again, what we're talking about is an integrated circuit that says if any one of these is a yes, then the answer out here will be a yes, and we're doing this with electrical charges. And that is an OR gate. And they're going to ask you, what is the relationship between the inputs and outputs of this particular OR gate? And what it says is any input being a 1 will give you a 1 output out here. Now let's do another one. Let's take a look at what is known as an exclusive OR gate. An exclusive OR gate looks like a boat with a trailer behind it. And an exclusive OR gate says that in order to produce a 1 output, it has to have these two inputs be dissimilar. They have to disagree with each other. And anytime they disagree with each other, then there will be a 1 output out here. And that's called an exclusive OR gate. Now let's take a look at the question. They're going to ask you about this on the test. They're going to show you several of these, and they're going to say which one of these is an exclusive OR gate. Well, what you do is you take a look at it. You know that the inputs have to disagree with each other. Well, this input here, the inputs don't disagree with each other. Here they disagree with each other, and the output is a 1. So that is an exclusive OR gate here. Here, they disagree with each other, but the output's a 0, so that's not a properly operating exclusive OR gate. So number 2 on this figure is a properly operating exclusive OR gate. And this is basically an integrated circuit to do this, and it's just a way of conveying information. Now, integrated circuits, as you know, often contain transistors, and it would be helpful to you on the test to understand how a transistor works. Here's a whole bunch of different kinds of transistors, but let's take a look inside a transistor and see if we can figure out how they work. Now, transistors, as you probably already know, are made of silicone material that are doped with another kind of material to change the characteristics of the silicon. And if they're doped with a certain kind of material, it's called, the silicon material becomes N-type silicon material. And in that particular case, N-type material has lots of free electrons in it. And P-type material, if it's doped with another substance, it becomes P-type material. And P-type material has lots of holes in which electrons can go. And you can use this information because you can construct an amplifier or a device to control the amount of current that flows through the transistor. And here's the way you'll do it. Let's assume that you have a transistor that's composed of N-type material here, P-type material here, and N-type material there. It's often referred to as a sandwich. And this is the junction between the N-type material and the P-type material. And that's a very important concept right there. Now, what you have to have is certain circumstances for current to flow through here, and here's what the circumstances are. Let's assume you put a negative charge over here, and let's assume you put a positive charge over here, and on the base, we're going to call this, by the way, the emitter, where there's a negative charge, because electrons are going to flow from the emitter through the base to the collector. And in order for current to flow, we need a negative charge here, a positive charge here. In order for current to flow, we also have to have a positive charge here, and here's why. If you put a negative charge here, what you're going to do is drive all the free electrons to this end. If there's a positive charge here, that means there will be holes available for those free electrons to flow, and electrons can flow across this junction. If, on the other hand, it was the other way around, let's assume you had a positive charge here and a negative charge here, then the electrons would be driven away from the junction and the holes, and the electrons could not flow across here. So in order for electrons to flow across through a transistor, the base has to have a different charge than the emitter. The emitter has a negative charge here. The base will have to have a positive charge in the case of NPN type of transistor, and then electrons will flow across. So this is an NPN transistor, and when this has a negative charge, that's the emitter, and the base has a positive charge, the junction is called forward biased. And forward biasing means that electricity will flow. A current will flow through the transistor. Now, another kind of transistor you might have would be, instead of an NPN transistor, would be a PNP transistor, and it's forward biased when the base is negative and the emitter is positive. And you can remember that because that's N negative and that's P positive. And that's how you remember it. So in order for a transistor to conduct electricity, it has to be forward biased. And on a PNP type of transistor, it's forward biased when the base is negative. So the middle of this sandwich is called the base. The part that sends off the electrons is called the emitter. And the part that you might think of as catching the electrons is called the collector. Now let's take a look at some questions they're going to ask you about that. And to do that, let's take a look at figure 22. And figure 22 is the symbol for a transistor in a schematic drawing. It's a symbol you would use in a schematic drawing for a transistor. And here we have a collector over here, and we have a base, and we have the emitter. Now notice the base is more positive than the emitter, and that's what you have to have in order for current to flow. And by the way, even though we said the electrons flow from the emitter to the collector, current is different than electrons. Just matter of convention, you say that current flows from positive to negative. We know electrons flow the opposite direction, but when you're talking about how current flows, it's said to flow from positive to negative. So this is a properly biased transistor right here because the base and the emitter have opposite charges from each other. Now let's take a look at the question they're going to ask you about this on the test. And the question they're going to ask you goes like this. They're going to show you these three and say which one of these has current flow. And it's properly set up transistor for current flow. And we've already said it's number one because the emitter and the base are opposite each other. And remember, current is always said to flow from positive to negative. So this is out because they got the current flow in the other direction. And down here, we have a negative base and a negative emitter, and that won't work. It's not forward biased. So drawing number one is a transistor that will allow current to flow. Now let's take a look at figure 23, and let's take a look at another question we're going to ask about electrical things involving a transistor, because here is a transistor right here at this point. And let's back off just a little bit more so that we can see this light up here, because really what we're trying to do is light that light up there. And what we're finding is that we have a negative ground here, and we have a battery over here with positive over here. And when we have current flowing through this whole assembly, we're going to light that light up there. Now let's take a look at it. We have here a transistor, and when there is a positive charge on the base, current will flow, because here we have a negative emitter, positive base, and a positive collector. So when there is a positive charge on the base, current will flow and the light will light. Now let's take a look at what we have here. We have here a rheostat, and we can tap off this resistor anywhere here, and if we tap off up on this direction more towards the positive pole of the battery, then we'll have a positive charge. If we pulled off down here, we'll have a less positive charge on the base. So we can control the amount of positive charge on the base by where we tap off. If we tap off closer to the positive pole of the battery, then we would have a positive charge on the base, current would flow, and the light would light. Now, a couple questions they're going to ask you. First of all, what would happen if you had an open here, and instead of having R1 shorting the ground as it does, you just had a complete open? Well, if you had a complete open, that you wouldn't have this flow to ground, and therefore you would have a very positive charge on this base, and what would happen is current would flow all the time. So the light couldn't be turned off. So if you had an open here at R1 instead of being a conduction to ground, if you had an open, then the light would be on all the time. You couldn't turn it off. Now, what would happen if R2 stuck in the up position? Well, the same thing would happen. The light would be on full bright because if you had R2 stuck in the up position, what happened is you'd move that tap on the rheostat closer to the positive end of the battery, and the light would be on all the time. So you can see now that being an A and P, it does make sense to understand transistors, because at least they're going to ask you this question on the test, and therefore you need to answer it on the test. And believe it or not, you and I have just covered everything that they're going to ask you about basic electricity on the A and P General Test.